Hello there and welcome to Life Beyond Scene, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're heading far south. Farther than the busy shipping lanes, farther than the warm holiday seas, farther than the gentle blue water people imagine when they hear the word ocean. We're going down toward the bottom of the map, where the water circles Antarctica without stopping, where the winds have room to build, where ice drifts like silent stone, and where the waves do not seem especially interested in making anyone feel welcome. Tonight's quiet journey is about the Southern Ocean, often called the most dangerous ocean in the world. Not because it has sea monsters, although if any ocean were allowed to have one, it would probably be this one. Not because it is the biggest ocean, because it is not. And not because it is the warmest, the busiest, or the most famous. The Southern Ocean is dangerous because it is remote, cold, restless, and unusually free. There are few land masses to interrupt its winds. There are few safe places to run when weather changes. There is ice above the water, ice below the water, and often more force in the waves than a ship would like to discuss. Before we go any farther, I would love to know where in the world are you listening from tonight, and how far are you from the nearest ocean? Are you near a coast, where the sea is part of daily life? Or are you far inland, where the ocean is something you mostly meet in pictures, maps, and the occasional documentary narrated by someone sounding very serious over footage of a penguin? And if you are listening late at night, tucked in somewhere warm, perhaps with a blanket, a pillow, or a cup of tea cooling nearby, there is something strangely comforting about learning of a place so wild from somewhere so safe. If you find the slow journey soothing, interesting, or just a gentle way to let the day loosen its grip, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of calm reach other curious minds who might enjoy drifting off with science, geography, and the occasional alarming fact delivered at a reasonable indoor volume. And I do hope this story of huge waves, fierce winds, and icy darkness does not keep you awake. But if it does, well, at least you will have a greater appreciation for your bed, which, as far as we know, is not currently being struck by a 12-metre swell. So, settle in, let your thoughts slow down, and picture the Earth from space. Imagine the familiar shapes of the continents: North America, South America, Africa, Australia, Asia, Europe. Then let your attention move downward. Past the tropics, past the temperate lands, past the islands and shipping routes, until the world narrows into the white mass of Antarctica. Around it, like a moving ring, lies the Southern Ocean. It does not sit neatly between continents like the Atlantic. It does not spread broadly across the warm centre of the planet like the Pacific. It wraps around the bottom of the world in a continuous loop, connecting the Atlantic, Indian and Pacific Oceans into one cold, circling system. That is one of the first things that makes the Southern Ocean unusual. Most oceans are partly held in place by land. They have edges, basins, coastlines and familiar entrances. The Southern Ocean has Antarctica at its centre, but around that icy continent the water can travel all the way around the globe. There is no giant wall of land to stop it, no continent placed conveniently in the way to say, "That is enough wind for today, thank you." So the wind keeps moving, the current keeps moving. The waves keep building. The whole region becomes a kind of open track around the planet, and the weather runs laps on it. For sailors, this has mattered for centuries. Long before satellites and modern forecasts, ships that ventured into the far southern latitudes entered a zone with a reputation. The names alone tell you plenty. The Roaring Forties, the Furious 50s, the Screaming 60s. These are not the names of cheerful holiday destinations. They describe bands of latitude in the southern hemisphere where strong westerly winds can sweep around the Earth with little land to slow them down. In the days of sail, those winds could be useful if they were behind you. A powerful wind could push a ship across the ocean with impressive speed, but the same wind could also turn against you, tear at sails, drive waves over the deck, and make every wooden plank in the vessel reconsider its career. The Southern Ocean is not dangerous in one simple way. It is dangerous through a combination of things. Cold makes every accident more serious. Distance makes every rescue harder. Wind makes the surface unpredictable. Ice creates hazards that do not always show themselves clearly. Waves can come from different directions. Storms can deepen quickly. A ship in warmer, calmer waters may have room for mistakes. In the Southern Ocean, small mistakes can become large ones very quickly. It is the kind of place where the sea does not need to be dramatic to be dangerous. It only needs to be itself, and yet there is no need to imagine it as evil or angry. The ocean is not trying to frighten anyone. It is not plotting against sailors in a cold underwater office. It is simply following physics. Air moves from high pressure to low pressure. Earth rotates. Water responds to wind. Currents carry heat, salt, nutrients, and drifting ice. Storms form and fade. Waves rise when wind transfers energy into the sea. The Southern Ocean is dangerous because the natural ingredients there line up in a very particular way. Give wind enough distance over water and the waves grow. Give storms cold air and strong pressure differences and they strengthen. Give the water a clear path around the world and the motion becomes enormous. One of the great engines of this motion is the Antarctic circumpolar current. That sounds like the sort of phrase that might appear in a school exam just when everyone was hoping for an easy question about dolphins. But the idea is simple enough. It is a massive current that flows around Antarctica, linking the major ocean basins. It is often described as the strongest ocean current on Earth, and it helps separate the cold Antarctic waters from warmer waters farther north. It is one of the reasons Antarctica remains so isolated and so icy. The current is not just moving water around a continent. It is helping organise the climate system of the whole planet, which is quite a large responsibility for something most of us have never seen in person. This current also makes the Southern Ocean different from the oceans we usually imagine. A beach ocean has waves arriving at the shore, gulls making unnecessary comments, and perhaps someone trying to keep sand out of a sandwich. The Southern Ocean is more like a moving boundary between worlds. It is where warmer waters from the north meet colder waters from the south. It is where deep water can rise toward the surface. It is where the atmosphere and the sea exchange heat and carbon dioxide on a huge scale. It is not just a dangerous ocean. It is a working ocean. A hard-working, cold-handed, sleep-deprived ocean, doing several planetary jobs at once. The danger, though, is what people tend to notice first. Imagine being on a ship down there. The horizon is not warm and golden, it is grey, wide, and often unsettled. The wind may not howl constantly, but it is rarely polite. The deck is wet. The air is sharp. The sea does not have that clear tropical blue of postcards. It is dark, heavy, and cold, sometimes almost metallic in appearance. Albatrosses may follow the ship, using the wind with a grace that makes human engineering look a little embarrassed. Far away, an iceberg might appear. At first, it may look small, just a pale shape in the distance. Then you remember that most of it is below the surface, and suddenly it becomes less like scenery and more like a floating instruction to pay attention. Ice is one of the Southern Ocean's most serious hazards. There are icebergs that have broken from glaciers or ice shelves. There is sea ice that forms when the ocean surface freezes. There are smaller chunks that can still damage a vessel. Ice can drift, scatter, close routes, and change with the season. It can look beautiful, and it often is beautiful, but beauty at sea is not the same as safety. A large iceberg in calm light can seem almost peaceful, with blue cracks, white walls, and strange shapes carved by waves and weather. But in poor visibility, with rough water and freezing spray, ice becomes a problem you may not see until it is far too close. Then there is the cold itself. Cold water is not just uncomfortable, it is dangerous in a direct and unforgiving way. In warm water, a person may have time. In Southern Ocean water, time becomes very short. The body loses heat quickly, muscles become weak, thinking becomes slower. Even with modern survival gear, the environment is severe. This is one reason the Southern Ocean has always carried a kind of seriousness among sailors, researchers, and expedition crews. Falling overboard anywhere is frightening. Falling overboard there is something every safety briefing would prefer you never test. The remoteness adds another layer. In many parts of the world, if something goes wrong at sea, help may be hours away. In the Southern Ocean, help may be days away, and those days may involve weather that does not feel cooperative. Search and rescue in such a place is difficult for everyone involved. Aircraft range, ship availability, storm conditions, ice, darkness, and distance all matter. Even today, with satellites, GPS, emergency beacons and advanced forecasting, the Southern Ocean remains a place where humans are small. Our tools are better than they used to be, but the ocean has not become smaller to match them. That is part of what makes this topic so fascinating. The Southern Ocean sits in a strange place in the human imagination. It is not unknown exactly. We have mapped it, crossed it, studied it, named its currents, measured its winds, and tracked its ice by satellite. And yet it still feels distant. Most people will never go there. Most people will never stand on a deck in those latitudes and feel the ship rise under them as a swell passes through. Most people will never see Antarctica appear beyond the water, white and enormous like the edge of a different world. For many of us, the Southern Ocean exists as a place on maps, a band of blue around the bottom, easy to overlook until someone reminds us that this band of blue helps run the planet. In recent years, more people have heard of the Southern Ocean, because it has been recognised more widely as the world's fifth ocean. That recognition is not because the water suddenly appeared one morning and asked for a name badge. Scientists and sailors had long understood that the waters around Antarctica behave differently from the waters farther north. The boundary is not just about geography, it is about circulation, temperature, ecology, and the great current that surrounds the continent. Calling it the Southern Ocean helps show that this is not merely the southern ends of the Atlantic, Pacific, and Indian Oceans. It is a distinct system with its own character, and frankly, quite a lot of attitude. The phrase, "world's most dangerous ocean," can sound dramatic, so it is worth being careful with it. Different oceans are dangerous in different ways. The North Atlantic has brutal storms and a long history of shipwrecks. The Indian Ocean has monsoons and cyclones. The Pacific can produce enormous storms, tsunamis, and vast distances. But the Southern Ocean has a combination that is hard to beat. It has the strongest current, some of the strongest winds, huge waves, freezing water, sea ice, icebergs, fast-changing weather, and very limited rescue options. If an ocean were being judged on a point system for difficulty, the Southern Ocean would not need to brag. It could simply hand over the paperwork and let everyone sit quietly for a moment. Still, danger is only one part of the story. If we only talk about the Southern Ocean as a threat, we miss what makes it important. It is also one of Earth's great climate regulators. It absorbs large amounts of heat and carbon dioxide. It helps move water between the surface and the deep ocean. It carries nutrients that support marine life. Tiny organisms living in its waters help feed krill, which feed penguins, seals, whales, fish, and seabirds. In a place that looks empty from far away, there is a whole living system at work, much of it hidden below the rough surface. The ocean may seem severe, but it is not lifeless. It is busy in a cold, efficient sort of way, like someone doing taxes in a snowstorm. There is something humbling about that. The Southern Ocean does not need palm trees or warm beaches to matter. It does not need to be easy to visit. It affects weather, climate, sea level, ecosystems, and global ocean circulation from a place most people will never see. It is both remote and connected. It is far away on the map, yet involved in the air we breathe, the heat the oceans store, and the changing future of the planet. That is a difficult idea to hold in the mind at first. A place can be distant from your home and still be part of your life. The Southern Ocean is one of those places. Tonight, we will move through it slowly. We will not rush straight into disaster stories, although there will certainly be ships, storms, ice and waves that behaved very badly. We will begin by understanding what the Southern Ocean actually is, because it is not just a ring of water with a dramatic reputation. Then we will look at why it is so wild, why the winds there have such famous names, how waves can grow to terrifying heights, how ice changes the rules of navigation, and how generations of sailors came to fear and respect those waters. We will also look beneath the surface, where strange and resilient life survives in the cold, and then we will come back to the bigger question of why this dangerous ocean matters to every other ocean and to us. For now, just picture it gently, not as a place you must survive, but as a place to understand. A dark ocean circling a white continent, wind moving over open water, swell travelling for thousands of kilometres, ice drifting in silence, birds riding the air above waves that would make most of us immediately remember an urgent appointment back on land. Somewhere down there, the planet is breathing through the sea, taking in heat, releasing cold, lifting deep water, sinking dense water, and keeping time in motions much older than any clock. And here you are, safe for the moment, listening from your own little corner of the world. Maybe the room is quiet. Maybe the day is ending. Maybe the nearest ocean is close enough to smell or so far away that it feels like another country. Either way, the Southern Ocean is turning beneath the southern sky, circling Antarctica as it has done for millions of years, rough, cold, powerful and deeply important. To understand why it became so feared, we first need to understand its shape, its boundaries, and the strange fact that this ocean is less like a bowl of water and more like a moving belt around the entire Earth. To picture the Southern Ocean properly, it helps to forget the way we usually imagine oceans for a moment. Most oceans sit between places. The Atlantic lies between the Americas and Europe and Africa. The Indian Ocean spreads between Africa, Asia, Australia and the cold waters farther south. The Pacific is enormous, of course, so enormous that it almost feels less like an ocean and more like the planet left a large space open and filled it with water. But even the Pacific has the Americas on one side and Asia and Australia on the other. It has a shape we can point to. It has edges that make sense on a map. The Southern Ocean is different. It does not sit between continents in the usual way. It wraps around one. It circles Antarctica in a continuous ring of water, wind and current. Stand above the Earth in your imagination and look down at the South Pole. Antarctica sits there in the middle, white, cold and heavy with ice. Around it the Southern Ocean moves like a huge belt. Not a belt made of leather, thankfully, because that would be a confusing day for geography, but a belt made of water that never truly stops turning. This is one reason the Southern Ocean can feel difficult to understand at first. It is not only a place, it is also a motion. You can draw a line around it on a map, and people often use the line of 60 degrees south latitude as a practical boundary. But the ocean itself is not obeying the line because it read a textbook. The real character of the Southern Ocean comes from the way its waters move, the way cold and warmer water meet, and the way the Antarctic circumpolar current flows around the continent. That current is one of the great moving features of Earth. It travels from west to east, all the way around Antarctica, linking the Atlantic, Indian and Pacific Oceans into one enormous circulating system. And that is a strange thing, really. We often talk about the oceans as though they are separate bodies, as though the Atlantic has its own office, the Pacific has a larger office with better windows, and the Indian Ocean is quietly getting on with things somewhere warm. But the oceans are connected. Water moves between them. Heat moves between them. Salt, nutrients, gases and living things move through them. The Southern Ocean makes that connection especially clear, because it touches the southern ends of the three great ocean basins and ties them together. This is why calling it the ocean that circles the planet is not an exaggeration. The current that defines much of its identity has no major continent blocking its path. Farther north, continents interrupt the flow of water. South America, Africa, Australia, and other land masses shape currents, redirect winds, and break the seas into basins. But around Antarctica, the water has a rare open route. It can keep going. Around and around it travels, driven by strong westerly winds and guided by Earth's rotation. Seafloor ridges, deep basins, and the shape of Antarctica itself. The Antarctic circumpolar current is often described as the strongest ocean current on Earth, and when you hear that, it is worth pausing for a second. We're not talking about a river you can stand beside, or a stream you can hop over if you're feeling confident and wearing shoes you do not care about. This current carries an astonishing volume of water. It is wide, deep, and powerful. In places, it stretches across thousands of kilometres. It is not a single neat ribbon of water, like a blue line drawn with a ruler. It is a broad shifting system with fronts, eddies, branches, and zones where waters of different temperatures and saltiness meet. The word front may sound like weather, and that's not a bad comparison. In the atmosphere, a front is where different air masses meet. In the ocean, fronts can mark boundaries between different water masses. In the Southern Ocean, these boundaries matter. Cold Antarctic water meets relatively warmer water from farther north. Dense water sinks. Deep water rises. Nutrients come toward the surface. The surface water exchanges heat and carbon dioxide with the air above. All of this is happening in a place that can look, from the deck of a ship, like nothing but grey water and bad manners. There is also the Antarctic convergence, sometimes called the polar front, where colder Antarctic waters meet warmer subantarctic waters. It is not a wall. You do not see a tidy line painted across the sea with a small sign saying, "Welcome, you are now cold." But it is a real boundary in the behaviour of the ocean. Cross it, and conditions shift. Water temperature changes. Marine life changes. The ocean becomes part of a different system. Sailors and scientists have long understood that the Southern Ocean is not just the southern edge of other oceans. It has its own structure. This is one reason its naming has sometimes caused debate. Some maps and institutions recognised the Southern Ocean long ago. Others treated the same waters as the southern parts of the Atlantic, Indian, and Pacific Oceans. In 2021, National Geographic formally recognised the Southern Ocean as the Fifth Ocean, which helped bring the name into wider public use. Of course, the water did not become more southern that morning. Penguins didn't gather near the ice and hold a small ceremony. But names matter, because they shape attention. When we name the Southern Ocean as its own ocean, we're saying that this region has its own physical identity and its own importance, and what an identity it has. It is the only ocean that completely circles the globe without being blocked by land. This makes it a kind of connector and divider at the same time. It connects the major ocean basins, allowing water and energy to move between them. But it also helps isolate Antarctica from warmer waters to the north. The Antarctic circumpolar current acts like a moving boundary around the continent. It helps keep Antarctica colder than it might otherwise be by limiting the easy movement of warmer surface waters southward. That does not mean Antarctica is protected from change. Not at all. The climate system is far more complicated than that. But the current has been a major part of why Antarctica developed and maintained such a cold, isolated environment. If you imagine the planet as a house, the Southern Ocean is something like the cold room at the bottom where all the pipes meet. Not a glamorous room perhaps, no one gives it a nice rug. But the whole house depends on what happens there. Deep currents connect through it. Heat is absorbed there. Carbon dioxide enters the ocean there. Nutrients are lifted there. The Southern Ocean is remote, but it is not separate. It is involved in the machinery of the whole climate system. This is where the idea of the Southern Ocean as a moving belt becomes useful. A belt moves things from one place to another. In a factory, A conveyor belt carries objects along a line. In the ocean, the comparison is not perfect, but it helps. The Southern Ocean helps move water between the surface and the deep ocean. Some deep waters rise there after travelling through the global ocean for long periods. When they reach the surface, they can exchange gases with the atmosphere. Some surface waters become cold and dense and sink again, carrying oxygen and carbon into the deep. This is part of the global overturning circulation, the large-scale movement of ocean water that helps distribute heat and chemicals around the planet. That sounds tidy when said in a sentence, but in reality it is messy, uneven, and constantly changing. The ocean does not move like a machine with clean metal parts. It swirls, it mixes, it pushes into ridges and around underwater plateaus. It forms eddies, which are rotating features that can trap and move water. It responds to winds, storms, ice, and the changing seasons. Scientists study these processes with ships, satellites, floating instruments, moorings, computer models, and more patience than most of us can imagine. The Southern Ocean is difficult to observe because it is remote and rough, so every measurement matters. A robot float drifting in those waters may not look heroic, but frankly it is doing field work most humans would rather read about from indoors. The shape of the seafloor also matters. We might think of the Southern Ocean as a surface, because that is what we see in photographs, but the ocean is three-dimensional. Beneath the waves are ridges, trenches, shelves, plateaus, and deep basins. These features steer the current. The Antarctic circumpolar current may seem free because it circles the globe, but it is still influenced by the bottom of the ocean. When the current crosses underwater ridges or squeezes through narrow passages, its flow can change. It can speed up, turn, mix, or create turbulence. The seafloor is not just sitting there quietly beneath the water, it is shaping the motion above it, like furniture in a dark room that everyone keeps bumping into. One of the most famous places in this circulating system is the Drake Passage, the stretch of ocean between the southern tip of South America and the Antarctic Peninsula. It is a narrow gap by Southern Ocean standards, although narrow here still means hundreds of kilometres, which is only narrow if you're an oceanographer or a very ambitious bird. The Drake Passage is known for rough seas because it sits in the path of the winds and currents circling Antarctica. Ships travelling to the Antarctic Peninsula often cross it, and many passengers quickly discover whether they truly enjoy adventure or merely liked the brochure. But the Drake Passage is not just a rough crossing, it is also a key gateway. The opening between South America and Antarctica allowed the Antarctic circumpolar current to flow around the continent. Over geological time, this helped shape Antarctica's climate isolation. The development of a circumpolar current is part of the long story of how Antarctica became the ice-covered continent we know today. The exact details involve plate tectonics, changing ocean gateways, atmospheric carbon dioxide, and other factors, so it is not as simple as one passage opening and the planet immediately saying, "Right, everyone put on a coat." But the connection between ocean circulation and Antarctic cooling is deeply important. The Southern Ocean also changes with the seasons in a way that can be hard to picture if you live far from polar regions. Around Antarctica, sea ice expands greatly in winter and retreats in summer. This does not mean the whole ocean freezes solid like a pond, which would be impressive but inconvenient for whales. Instead, the surface freezes into sea ice over large areas, then melts back as sunlight returns and temperatures rise. This seasonal breathing of ice changes how the ocean and atmosphere interact. Ice reflects sunlight, insulates the ocean from the air, affects saltiness as it forms and melts, and creates habitat for organisms that have adapted to life around ice. When sea ice forms, it rejects salt into the water below, making that water saltier and denser. Dense water can sink, contributing to deep water formation in some regions around Antarctica. When sea ice melts, it freshens the surface. These processes influence layering in the ocean, which in turn affects mixing, nutrients, and heat movement. So even the ice that seems to float quietly at the surface is part of a larger set of processes. It is not just frozen scenery. It is an active part of the system. This brings us back to why the Southern Ocean is not only dangerous for ships, but important for everyone. The same features that make it wild also make it powerful in the climate system. The strong winds stir and drive the surface. The current links ocean basins. The cold water takes part in deep circulation. The region absorbs heat and carbon dioxide from the atmosphere. The upwelling of deep water brings nutrients to the surface, helping support phytoplankton, tiny organisms that form the base of much of the marine food web. These tiny organisms may not look dramatic, especially compared with an iceberg or a storm wave, but they are essential. Many large animals in the Southern Ocean depend, directly or indirectly, on productivity that begins with microscopic life. It is a useful reminder that size can mislead us. A blue whale is enormous and easy to admire. A penguin is charming and looks like it is late for a meeting. A seal has the relaxed confidence of an animal that knows it is good at swimming, but beneath the surface, small organisms are doing the basic work of turning sunlight, nutrients, and carbon into life. Krill feed on phytoplankton. Penguins, seals, fish, whales, and seabirds feed on krill or on animals connected to krill. The Southern Ocean food web has many details, but krill are famously central to it. The ocean that looks empty and harsh from above can be full of feeding, migration, growth, and survival below. Still, its circling nature remains the key idea. Most currents have beginning and end points that make sense in relation to continents and basins. The Antarctic circumpolar current simply keeps going around. That has consequences for waves as well as water movement. Because the Southern Ocean is not broken up by major land masses, winds can blow across very long stretches of open water. This stretch is called fetch. The longer the fetch, and the stronger and longer lasting the wind, the more energy can be transferred into waves. That is one reason the Southern Ocean is known for huge seas. The water has room to build itself into something serious. The circling also means storms can travel with fewer interruptions. Weather systems move through the southern latitudes, and the ocean responds. Low-pressure systems deepen, winds strengthen, swell spreads outward, conditions can change quickly. A vessel may deal not only with waves made by local wind, but also swell arriving from distant storms. Waves from different directions can meet and create confused seas. To anyone who prefers water to stay politely in a glass, this is not an encouraging situation, and yet this constant motion is also part of the ocean's role. The Southern Ocean mixes the planet's waters in ways that matter far beyond Antarctica. It is a meeting place of ocean basins. Water that has been in the Atlantic can be carried toward the Indian and Pacific sectors. Deep water can return toward the surface. Surface water can sink and spread. The Southern Ocean is like a great roundabout, although one with freezing spray, no lane markings, and several albatrosses judging your steering. Water enters, changes, and leaves, carrying with it heat, salt, nutrients, carbon, and oxygen. For scientists, this makes the Southern Ocean both fascinating and frustrating. It is central to understanding climate, but hard to measure. It is vast, stormy, and remote. Winter darkness and sea ice make research even more difficult. Ships can only be in certain places at certain times, and no ship can cover everything. Satellites are extremely useful, but they mostly observe the surface and can have trouble with clouds, darkness, and ice. Autonomous floats and gliders have improved our view, but even modern instruments face a demanding environment. The Southern Ocean does not hand over its data easily. It makes researchers work for it, like a teacher who believes character is built through cold fingers. The more we learn, the more clearly we see that this ocean is not a blank ring around Antarctica. It has regions with different behaviours. The Weddell Sea, the Ross Sea, the Amundsen Sea, the Bellingshausen Sea and other sectors each have their own patterns of ice, water, wind and biology. The Antarctic Peninsula is warming differently from East Antarctica. West Antarctic ice shelves interact with relatively warm deep water in ways that concern glaciologists. The Indian, Pacific and Atlantic sectors of the Southern Ocean do not behave identically. So when we say the Southern Ocean, we are naming one connected system, but within it are many local stories. This is similar to saying the forest. A forest may be one place on a map, but every hollow, ridge, stream and clearing has its own conditions. The Southern Ocean is the same, only wetter, colder, and much less convenient for a picnic. A current may circle the entire continent, but the details shift from one region to another. Some places are shaped by broad open water, others are shaped by sea ice, others by nearby ice shelves, underwater canyons, or the shelves around Antarctica. The ocean is connected, but it is not uniform. That matters when we talk about danger. The Southern Ocean's dangerous reputation does not come from a single hazard, repeated everywhere in exactly the same way. In one place, the main concern may be sea ice. In another, it may be swell. In another, katabatic winds flowing off Antarctica can suddenly make conditions worse near the coast. In another, icebergs may drift into shipping routes. In another, the problem may simply be distance. Even a manageable mechanical issue becomes more serious when the nearest major port is very far away and the weather between here and there has opinions. The fact that the Southern Ocean circles the planet also affects the way people encounter it. There is no one entrance. Some approach from South America toward the Antarctic Peninsula. Others come from New Zealand toward the Ross Sea. Others travel south from South Africa or Australia into the Indian Ocean sector. Each route has its own character, but all eventually bring the traveller into the same broad belt of southern water. It is a rare ocean that can be reached from several directions and still feel like one connected place. For centuries, this circling ocean shaped human exploration. Early navigators trying to find southern lands, sealers and whalers seeking profit, scientific expeditions seeking knowledge, and modern research ships all had to deal with the same basic fact. Antarctica is surrounded by water that moves and weather that does not care much about human schedules. The Southern Ocean was not merely something to cross on the way to Antarctica. It was part of the challenge, part of the mystery, and sometimes part of the tragedy. Even now, with modern engines and navigation, there is a psychological shift when a ship enters those waters. The map begins to look emptier, ports vanish behind you. The forecast becomes more important. The horizon feels wider. People who work there understand that the Southern Ocean deserves respect, not because it is magical or angry, but because it is large, cold, and physically powerful. Respect at sea is often just another word for remembering that physics always gets the final vote. The ocean's circular path also gives it a strange kind of independence. In other parts of the world, humans have heavily shaped coastlines with ports, cities, canals, fishing fleets, oil platforms and shipping lanes. The Southern Ocean is not untouched, but it is less directly crowded. Its human presence is scattered. Research stations are mostly on land or islands. Fishing occurs in certain regions. Tourist ships visit parts of Antarctica. But compared with many northern seas, the Southern Ocean still feels distant from everyday human noise. The dominant forces remain wind, ice, current, and season. That does not mean humans have little influence there. Quite the opposite. Climate change reaches the Southern Ocean through warming air, warming water, changing winds, changing sea ice, ocean acidification, and impacts on ecosystems. The ocean may be remote from cities, but it is not remote from the atmosphere. Carbon dioxide released anywhere mixes through the air. Heat added to the climate system enters the ocean. The Southern Ocean absorbs a major share of that heat and carbon, which means it has been buffering the rest of the planet. But buffering is not the same as being unaffected. A sponge can absorb water, but eventually you should ask how the sponge is doing. This is why the Southern Ocean shape matters so much, because it circles the planet, it acts on a planetary scale. Changes in its winds, currents, ice, or capacity to absorb heat and carbon can affect global systems. A shift in deep water formation can influence ocean circulation. Changes in sea ice can alter how much sunlight is reflected or absorbed. Changes in nutrient supply can affect marine productivity. Changes around Antarctica's ice shelves can influence ice loss and sea level rise. The ring of water around Antarctica is not a distant decoration at the bottom of the globe. It is connected to the rest of the Earth in practical, measurable ways. Maps can hide this from us. On many world maps, Antarctica is stretched along the bottom or cut off entirely, as though the lower edge of the page simply got tired. The Southern Ocean may appear as a blue strip at the bottom, easy to ignore, but on a globe it becomes clearer. There is Antarctica, and around it is an uninterrupted oceanic ring. That ring is not at the edge of the world. A globe has no edge. It is part of the whole system. The Southern Ocean only seems far away because most people live much farther north. So, when we call it the ocean that circles the planet, we're describing both its geography and its function. It circles Antarctica physically. It links the other oceans dynamically. It helps move heat, carbon, nutrients, and deep water through the global ocean. It separates and connects at the same time. It is the boundary around Antarctica and the meeting place of the world's seas. And because nothing stops it for very long, the forces there can grow large. Wind has room. Waves have room. Currents have room. Storms have room. That is rarely a recipe for calm. There is something useful in seeing the Southern Ocean this way before we talk about its worst weather. If we begin only with storms, it becomes a place of danger and nothing more. But if we begin with its shape and motion, the danger starts to make sense. The winds are not random. The waves are not just bad luck. The current is not merely a line on a diagram. They are all connected to the same basic fact. Around Antarctica, the planet gives the ocean space to move. And once an ocean has that kind of space, the next thing to understand is the wind. Not a light breeze, not the sort that gently moves a curtain near an open window, but the powerful westerly winds that sweep through the far southern latitudes. These winds have helped give the Southern Ocean its reputation, its motion, and its long history of frightening sailors who would have strongly preferred a calmer career, perhaps in accounting. The wildness begins with space. That may sound too simple for an ocean with such a dramatic reputation, but it is the first thing to understand. The Southern Ocean has room to become itself. Around Antarctica, the sea is not constantly interrupted by continents, narrow enclosed basins, warm islands, busy coastlines, or friendly harbours appearing just when everyone on board would like a little break. It circles the bottom of the world with a kind of physical freedom that most oceans do not have, and when water, wind, and weather are given that much open distance, they can build into something very serious. Think about wind blowing across a small pond. It may ruffle the surface, push a few little ripples toward the reeds, and slightly annoy a duck. Now think about wind blowing across hundreds or even thousands of miles of open ocean, with no mountain range, city, forest, or continent in the way. The wind has time to grip the sea. It presses on the surface again and again. It transfers energy into the water. Small ripples become waves. Waves gather height and length. Swell begins to travel beyond the storm that created it. And in the Southern Ocean, this process can happen over some of the longest open stretches of water on Earth. This open distance is called fetch. It is a plain word, but an important one. Fetch means the distance over water that the wind can blow without interruption. The stronger the wind, the longer it blows, and the greater the fetch, the larger the waves can become. In many parts of the world, land gets in the way before the sea can fully develop. Around Antarctica, the wind often gets a much longer invitation. It can run over open water for a very long way, building seas that are not merely choppy or uncomfortable, but genuinely intimidating. The Southern Ocean does not need to perform tricks to be dangerous. It just needs wind, distance, and time. Unfortunately, it has plenty of all three. But the question remains, why are the winds there so strong in the first place? The answer begins with temperature. Earth is unevenly heated by the sun. The tropics receive more direct sunlight, while the polar regions receive less. This creates a large temperature difference between the warmer lower latitudes and the cold Antarctic region. Air responds to that difference. Warm air, cold air, pressure differences, and Earth's rotation all combine to create large-scale wind patterns. In the southern hemisphere, these winds sweep around the planet in powerful bands, especially over the open ocean surrounding Antarctica. Earth's rotation matters because moving air does not simply travel in a straight line from one place to another. It is deflected by the Coriolis effect. In the southern hemisphere, moving air is deflected to the left of its path. This helps shape the broad westerly winds that blow from west to east across the southern latitudes. These are the winds sailors came to know with deep respect, and probably a few words not suitable for a calm educational video. They are part of the reason the Southern Ocean has famous names attached to its latitudes, names that sound less like geography and more like warnings. The Southern Ocean sits beneath a belt of frequent low-pressure systems and storms. Low pressure is associated with rising air, unsettled weather, and wind. Around Antarctica, strong contrasts between cold polar air and warmer air farther north help create conditions where storms can form and move. These storms often travel from west to east, pushed along by the prevailing winds. One storm passes, then another follows, then another, like a queue of bad moods forming over the ocean. The result is a region where rough weather is not an occasional visitor. It is a regular part of life. In warmer oceans, a storm may still be dangerous, of course. No ocean has ever signed an agreement to remain calm for human convenience. But the Southern Ocean adds its own set of complications. The air is cold. The water is cold. The waves can be long and powerful. The storms have space to travel. Ice may be present. Visibility can drop. The nearest safe harbour may be very far away. A ship cannot simply pull over, wait for better conditions and get a pastry. It must keep existing in the weather, which is not always as easy as that sentence makes it sound. Then there is the Antarctic Circumpolar Current, the huge ocean current that flows around Antarctica. This current is not the same thing as the wind, but the two are linked. The westerly winds help drive the surface waters, and the current responds as part of a much larger ocean system. The current connects the Atlantic, Indian and Pacific Oceans, and moves a vast amount of water around the planet. It is often described as the strongest current on Earth. That is an impressive title, although perhaps not one you want to encounter while trying to keep your soup inside a bowl on a rolling ship. The current adds to the Southern Ocean's restless nature. It does not make every wave by itself, and it is not the only reason storms are severe, but it is part of the moving system. Where strong current, wind, and swell interact, the sea can become confused. Waves may come from more than one direction. Local wind waves may meet older swell from distant storms. Currents can steepen waves in some conditions. A vessel may rise and fall in one rhythm, then be struck from another angle by a different set of waves, as though the ocean has decided that one pattern was too predictable. This is one of the reasons sailors often describe Southern Ocean seas as difficult, not just large. A very long swell from one direction can be uncomfortable but manageable if it is regular. A steep, breaking sea from multiple directions is much harder. The ship pitches, rolls, shudders, and occasionally behaves as if it has remembered an old grudge. Decks flood, equipment strains. Crew members move carefully, because the floor beneath them is not fully committed to being a floor. In such conditions, every simple task becomes more complicated. Making tea becomes a minor engineering project. Sleeping becomes an act of negotiation. Walking across a room requires the focus of someone defusing a small bomb. The Southern Ocean also has a special relationship with cold. Cold air can make storms sharper. Cold water makes survival harder. Freezing spray can build on exposed surfaces of ships, adding weight and creating hazards. Sea ice and icebergs introduce obstacles that do not behave like fixed land. They drift, break, melt, rotate, and sometimes hide most of their mass beneath the water. A coastline stays where it is, which is thoughtful. Ice does not always show the same courtesy. Cold also changes the stakes of any accident. A wave breaking over the deck in warm water is dangerous. A wave breaking over the deck in freezing conditions is dangerous and exhausting. Wet clothing steals heat. Fingers become clumsy. Metal surfaces become painful to touch. Lines stiffen. Visibility can worsen. People get tired faster. Machines may perform less reliably. The Southern Ocean is not just wild because it is dramatic. It is wild because it gives very little margin for error. The remoteness makes that margin even smaller. In many seas, danger is softened by proximity. There may be ports, coast guards, nearby vessels, aircraft, or at least a shipping lane where help can arrive in a reasonable time. In the Southern Ocean, help can be distant. Rescue is possible, and modern technology has improved safety greatly, but distance is still distance. A storm does not become kinder because a satellite knows where you are. A rescue ship still has to cross the water. An aircraft still has range limits. Weather still decides whether operations are possible. In remote southern waters, the environment can turn a problem into a crisis simply by refusing to be near anything convenient. This remoteness affects the mind as well. People who work in the Southern Ocean often describe the feeling of being far from the ordinary world. The map becomes empty. The horizon is wide. The sky is low and fast-moving. There are no familiar landmarks, no city lights, no coastline just over there waiting with warm food and dry socks. Human beings are adaptable, but we are still land animals with a strong appreciation for stable surfaces. The Southern Ocean reminds us of that rather quickly. Another reason the ocean is so wild is that the atmosphere and ocean there are tightly connected. The winds push the surface. The surface responds with waves and currents. Storms change pressure and temperature. The ocean releases and absorbs heat. Sea ice forms and melts. Deep water rises toward the surface in some regions, bringing nutrients and carbon-rich water upward. Surface waters can cool, become denser, and sink. These exchanges happen across huge areas. The Southern Ocean is not just a rough surface. It is a place where the air and sea are constantly working on each other. That upwelling of deep water is especially important. In parts of the Southern Ocean, winds and currents help draw deep water toward the surface. This water may have been away from the atmosphere for a long time. When it comes up, it can carry heat, nutrients, and dissolved carbon. Nutrients can feed phytoplankton, the tiny plant-like organisms at the base of the food web. Carbon and heat can be exchanged with the atmosphere. The same winds that help make the ocean dangerous also help make it productive and important to the planet's climate system. So the Southern Ocean is not simply wild in the sense of rough. It is active. It is doing a lot at once, and most of that work is not visible from the surface. There is a practical lesson here. The Southern Ocean's violence is not random. It is not a moody personality trait. It is the result of several physical factors lining up. A cold continent at the centre, warmer latitudes farther north, a rotating Earth, strong pressure differences, prevailing westerly winds, very long fetch, a powerful circumpolar current, frequent storms, ice, deep water exchange, remote geography. Put those together and you get an ocean where rough conditions are not surprising. Calm becomes the surprise. Calm is the guest everyone likes but nobody fully trusts, because it may leave without saying goodbye. Near Antarctica itself, another kind of wind can enter the story. Katabatic winds form when cold, dense air flows downhill from the Antarctic ice sheet toward the coast. Antarctica is high. icy, and extremely cold. Air over the ice can cool, become dense, and slide downward under gravity. When that air reaches coastal regions, it can accelerate through valleys or gaps in the terrain. These winds can be fierce. They may not define the entire open Southern Ocean in the same way as the broad westerlies, but near the Antarctic coast they can create sudden and hazardous conditions. Imagine the continent itself exhaling cold air down toward the sea, not in a mystical way, just gravity, density, slope and temperature doing exactly what physics allows. Still, if you're in a small boat near the coast, the distinction may not be emotionally comforting. The Southern Ocean's weather is also shaped by the lack of large land masses in the southern mid-latitudes. In the northern hemisphere, continents break up the flow of air and water. Mountains, forests, deserts, and cities all affect weather patterns. In the southern hemisphere, especially between about 40 and 60 degrees south, there is much more ocean. This allows winds to circle more freely. It also means storms can travel over water for long distances, maintaining access to moisture and energy. The atmosphere does not have to deal with as many interruptions. It can keep moving, keep deepening, keep building seas beneath it. This is why the Southern Ocean can feel relentless. It is not always in a state of full storm. There are calmer periods, clearer days, and moments of strange beauty. But the underlying system is energetic. Weather changes can be fast. Forecasts matter enormously, but even good forecasts cannot make the ocean gentle. They only help people prepare for what is coming. And sometimes what is coming is a low-pressure system with strong winds, heavy seas, and the general attitude of a washing machine full of bricks. There is also a seasonal rhythm. Winter in the Southern Ocean is especially harsh. The belt of storms can intensify. Darkness increases at high latitudes. Sea ice expands around Antarctica. Temperatures drop. Conditions become more difficult for ships and research operations. Summer brings more light and less sea ice in many regions, but it does not turn the Southern Ocean into a calm vacation lake. The winds still blow. Swell still travels. Icebergs still drift. A person can visit in the gentler season and still come away with a very sincere respect for handrails. The waves deserve careful attention because they are one of the clearest expressions of the ocean's wildness. Waves are built by wind, but once formed, swell can travel far beyond the storm that made it. In the Southern Ocean, waves can be long, powerful, and fast-moving. A ship may be dealing with wind from one system, while swell from an earlier storm rolls in from somewhere else. The result can be a complicated sea state. A large wave is not always the only issue. The spacing, direction, steepness, and braking behaviour all matter. A long swell may lift a ship smoothly. A steep braking wave can hit with violent force. A confused sea can make motion unpredictable, which is unpleasant for people, cargo, equipment, and anyone attempting to carry a tray. Rogue waves are also part of the fear surrounding extreme seas, though they are often misunderstood. A rogue wave is not just a big wave. It is usually defined as a wave that is more than twice the significant wave height, meaning it is unusually large compared with the surrounding sea state. In rough regions like the Southern Ocean, where storms, swells, currents, and long fetch can interact, unusually large individual waves can occur. They are rare, but they are real enough to be taken seriously. For sailors, the important point is not whether every frightening wave is technically rogue. The important point is that the ocean can produce individual waves far larger than the average waves around them, and averages are not what break windows on a bridge. Ice makes wave behaviour even more complicated. Sea ice can dampen waves by absorbing energy, but broken ice fields, marginal ice zones, and open water near ice can create difficult navigation. Icebergs can appear in areas of open water. Smaller pieces may be harder to detect, especially in rough seas or poor visibility. Radar can help, but conditions matter. Fog, snow, darkness, and spray all reduce the simple human ability to see what is ahead. And since icebergs have most of their mass underwater, what you see is only part of the problem. It is a little like meeting someone at a party and discovering later that they brought an entire hidden orchestra with them. The Southern Ocean is wild in another sense too. It is one of the few places where the scale of nature still overwhelms ordinary human assumptions. Many environments can be controlled or softened by infrastructure. Rivers can be bridged, roads can be built through mountains, weather can be predicted, buildings can be heated, harbours can be protected. But the Southern Ocean remains difficult to domesticate. You may travel through it with steel, engines, satellite communication, and weather models, but you're still entering a moving environment larger than anything you control. The best approach is not domination. It is preparation, caution, and respect. That respect is shared by scientists as much as sailors. To study the Southern Ocean, researchers need instruments that can survive rough seas, cold, pressure, and ice. Ships must be built and operated carefully. Autonomous floats must endure months or years of drifting. Moorings must sit in place while currents pull and storms pass overhead. Satellites must help fill gaps because no ship can be everywhere. Even collecting a simple measurement in the Southern Ocean can involve planning, expense, and risk. A graph in a scientific paper may look clean and calm, but somewhere behind it there may have been a deck covered in spray, a person in waterproof gear, and a machine refusing to cooperate because it was very cold and had chosen drama. The wildness also has consequences beyond the region. Strong winds and rough seas influence how much heat and gas move between the ocean and atmosphere. Mixing brings different layers of water into contact. Upwelling supplies nutrients. The ocean's ability to absorb carbon dioxide affects climate. The Southern Ocean has taken up a significant amount of human-produced carbon dioxide and heat, helping slow the full effect of warming in the atmosphere. But that does not mean it can absorb endlessly without change. The same system that buffers the planet can also shift in response to changing winds, warming water, melting ice, and changing sea ice cover. So, when we ask why the Southern Ocean is so wild, the answer is not one sentence. It is a chain. The planet is unevenly heated. Air moves. Earth rotates. Winds form. The lack of land lets these winds strengthen and continue. Wind pushes water. Waves build over long fetch. The Antarctic circumpolar current moves around the continent. Storms travel through the region. Cold raises the risk. Ice adds hazards. Distance reduces rescue options. The ocean and atmosphere exchange heat, carbon and energy across a vast moving surface. Nothing about this system is decorative. Every part contributes. And yet, for all its severity, the Southern Ocean is not chaos. It has patterns, it has seasons, it has currents, fronts, storm tracks, and physical rules. It can be studied, measured, and partly predicted. The danger comes not from disorder, but from power. A powerful system can still be organised. A storm can follow physics precisely and still ruin your afternoon. A current can be part of a stable global circulation and still make navigation difficult. A wave can be mathematically explainable and still be very bad news for a person standing in the wrong place. That may be the most important thing to hold in mind as we move deeper into its story. The Southern Ocean is wild because it is one of the clearest places on Earth where large-scale planetary forces meet without much interruption. Temperature differences, rotation, wind, water, ice, and distance all express themselves there with unusual strength. It is not separate from the rest of the world. It is the rest of the world moving through one severe region. The same atmosphere that brings a breeze to your window is connected to the winds that circle Antarctica. The same ocean system that shapes climate elsewhere runs through these waters. The Southern Ocean is far away, but it is not detached. From here, the story naturally turns to the wind belts that gave these latitudes their famous names. Sailors did not call them calm, pleasant, and mildly inconvenient. They called them the Roaring Forties, the Furious 50s, and the Screaming 60s, which tells you that by the time humans started naming these regions, the ocean had already made quite an impression. Those names sound almost too dramatic to be real, don't they? The Roaring 40s, the Furious 50s, and the Screaming 60s. They sound less like bands of latitude and more like three relatives you avoid sitting near at a family dinner. And yet, they are real names used by sailors, weather watchers, oceanographers, and anyone with a healthy respect for wind that has been given enough room to misbehave. These names refer to parts of the southern hemisphere, roughly between 40 and 70 degrees south. The Roaring 40s sit between about 40 and 50 degrees south. Below them come the Furious 50s, between about 50 and 60 degrees south. Then, closer to Antarctica, are the Screaming 60s, between about 60 and 70 degrees south. The farther south you go, the colder, more remote and more ice-filled the world becomes. The names are not official lines painted on the sea, of course. The ocean does not stop at 50 degrees south and say, right, time to become furious. But the names are useful because they capture what sailors experienced there for centuries. Strong winds, rough seas, sudden weather, long swells, cold air, and the feeling that the planet had turned the volume up. The Roaring 40s were the first of these southern wind belts that many sailors came to know well. In the age of sail, they were feared, but they were also useful. A sailing ship needed wind. Without wind, it could sit still for days or weeks, creaking gently on an empty sea while everyone on board slowly reconsidered every decision that had led them there. The Roaring 40s offered powerful westerly winds that could push ships eastward across the southern hemisphere. For vessels travelling between Europe, southern Africa, Australia, New Zealand, and parts of Asia, these winds could shorten voyages. They were not comfortable, but they were practical. A bit like a very stern coach shouting at you to run faster across the ocean. The basic reason for these winds is not mysterious, although the experience of being inside them certainly can feel that way. Warm air near the equator rises and moves poleward high in the atmosphere. Cooler air moves in other parts of the circulation. Earth's rotation bends these movements, shaping global wind belts. In the southern hemisphere, the winds in these latitudes blow mainly from west to east. That already sets the stage. But what makes the southern wind so famous is the lack of land. In the northern hemisphere, big continents interrupt the air. North America, Europe, and Asia stand in the way. Mountains, forests, deserts, cities, and coastlines all disturb the flow. In the southern hemisphere, at these latitudes, there is much more ocean. South of Africa, Australia, and South America, the air can keep going. It circles the planet with fewer interruptions, gathering strength over cold water and open distance. The Roaring 40s are not roaring every second of every day. That is worth saying clearly, because names like these can make the whole region sound like a permanent disaster. The winds shift, storms pass, calm periods happen. Some days may be surprisingly manageable. A sailor might even enjoy a stretch of steady wind and good progress, perhaps with the cautious happiness of someone petting a large dog that might still bite. But the general pattern is strong and unsettled enough that the name stuck. Over time, sailors learned that around 40 degrees south, the sea and wind began to change. The ocean felt less sheltered, the weather moved faster, and the waves had more room to grow. One of the old sailing routes that used these winds was the Clipper route. Fast sailing ships heading from Europe toward Australia could travel south into the westerlies, catch the powerful eastward winds, and race across the Southern Ocean. The route could be quicker than staying farther north, but speed came with danger. These ships were made of wood and canvas, guided by human skill, experience, and a great deal of nerve. The crew faced cold, wet decks, heavy seas, and the constant risk of damage to sails, rigging, or hull. The wind that helped a ship move quickly could also tear it apart if handled badly, or if the weather simply became too much. It was a bargain with the ocean, and the ocean did not always honour the cheerful parts of the agreement. Below the Roaring 40s are the Furious 50s. The name does not soften things. It does not suggest that after all that roaring, the ocean becomes thoughtful and reflective. Around 50 degrees south, the world becomes more remote, colder and often rougher. Land is even scarcer. The winds continue their eastward flow, and storms can sweep around the planet with impressive freedom. The seas here can become large, steep and confused, especially when local winds meet swell from distant storms. For sailors, the furious 50s have long meant serious water. This is not the place for loose equipment, careless footing, or pretending you will just pop outside for a moment without proper gear. The furious 50s also carry a psychological weight. On a map, 10 degrees of latitude may look simple. Just move the finger down a little. There we are, easy. But at sea, each degree south can feel like a commitment. The air cools, the weather sharpens, the daylight changes with the season. The nearest safe harbour may be very far away. Ships travelling through these waters are not just moving through coordinates. They are moving through a region where the atmosphere and ocean are working at large scale. A person on deck can feel that difference in the body. The wind pushes harder, spray stings the face, the ship's motion becomes more forceful. Even the colour of the sea can seem darker and more serious, although the sea, to be fair, has never been known for smiling. Then come the screaming 60s. By this point we are near the latitudes that approach Antarctica itself. These waters are colder, more isolated, and often affected by sea ice and icebergs. The name suggests constant shrieking wind, and while conditions vary, the reputation is well earned. The Southern Ocean, close to 60 degrees south, is a place where weather, ice, current, and remoteness combine. It is not simply that the wind is strong, it is that the consequences of strong wind become greater. Waves grow in cold water, ice may be near, visibility may change, rescue becomes more difficult. A storm in the screaming 60s is not just an unpleasant weather event, it is an entire environment becoming hostile at once. It is important to understand that these three zones are connected. They are not three separate rooms in the ocean with different curtains. They are part of the broad band of southern hemisphere westerlies. These winds shift north and south with the seasons. They strengthen and weaken with weather patterns. They interact with ocean currents, sea surface temperatures, and pressure systems. They are not fixed like a road. They are moving belts of air. But sailors gave them names because repeated experience matters. If enough people cross the same waters and come back saying, "That was loud," the name Roaring Forties begins to make sense. The names also tell us something about human memory. Sailors did not call them the useful 40s, the slightly annoying 50s, and the rather brisk 60s. They named them from the experience of being there. Wind at sea is not just a number on a weather chart. It is sound, pressure, motion, and labour. It is the rigging humming. It is waves hitting the hull. It is rain or spray blown sideways. It is the cook trying to prepare food in a galley that is moving in several directions at once. It is the sleeping sailor being rolled against the side of a bunk for the 10th time and quietly losing faith in furniture. These names came from bodies, not just instruments. In the days before modern forecasting, entering these latitudes required judgment and courage. Sailors watched the sky, the swell, the barometer, the clouds, the birds, and the behaviour of the ship. They learned to read signs. A falling barometer could warn of a storm. A changing swell could hint at distant weather. Clouds could show movement and pressure. But even skilled crews were limited by what they could observe from one point on a huge ocean. Today, satellites can watch entire weather systems. Forecast models can predict storm tracks. Ships receive warnings. But earlier sailors had far less information. They moved through the wind belts with experience, instinct, and sometimes luck, which is useful but not a proper safety system. The lack of land is again the key. In the northern hemisphere, if a storm travels eastward, it often crosses continents and changes. Land affects temperature, moisture, friction, and pressure. Mountains can disrupt flow. Coastlines can reshape weather. In the southern hemisphere's middle and high latitudes, the atmosphere has fewer obstacles. Air moves over ocean after ocean. This helps create the strong westerly flow that defines the region. It also allows storms to travel long distances and maintain strength. A low-pressure system can move around the Southern Ocean, like it has been given a wide road and very little traffic. This also affects the waves. Wind blowing over open ocean transfers energy into the sea. The longer the wind blows and the farther it blows over water, the more waves can develop. In the roaring 40s, furious 50s and screaming 60s, long fetch helps create powerful seas. Waves generated by one storm can travel far away as swell. Then another storm may create new waves from another direction. A ship can find itself in a sea where different wave systems overlap. This can make the motion irregular and hard to predict. A wave from the side, a swell from behind, a steep sea from ahead. The ocean becomes less like a regular rise and fall, and more like being carried by a very large animal that has not agreed to be ridden. The Southern Ocean's current system also plays into this. The Antarctic circumpolar current flows around Antarctica in the same broad west to east direction as the prevailing winds. The wind helps drive it, and the current interacts with the atmosphere above and the seafloor below. Where currents and waves meet in certain ways, seas can steepen or become more confused. Not every rough wave is caused by current, and not every current produces dramatic waves at the surface. But in the Southern Ocean, wind, current, storm tracks, and seafloor features are all part of the same restless machinery. The result is a place where the water rarely feels simple. For the crews of sailing ships, this machinery could be both a gift and a threat. A ship using the roaring 40s could make excellent speed eastward. The winds were dependable enough to shape trade routes. Clippers carrying wool, gold, passengers or cargo might push hard through the southern latitudes, trying to complete voyages quickly. Speed mattered, money mattered, reputation mattered. A fast passage could make a captain famous. But the price was exposure to some of the harshest seas on Earth. The same wind that filled the sails could drive the ship toward danger. Too much canvas in rising wind could break masts or tear sails. Too little canvas could leave the ship struggling in heavy seas. Decisions had to be made quickly, often in terrible conditions. There is a particular kind of danger in useful danger. A reef or rock is clearly bad. You avoid it. A fire is clearly bad. You put it out. But strong wind can be useful until suddenly it is not. It can move the ship beautifully for hours, then strengthen until the crew must reduce sail, secure everything, and endure. That makes the Roaring 40s and Furious 50s especially complicated in maritime history. They were not simply avoided, they were used. Sailors chose to enter them because the reward could be great. It is a little like accepting a ride from someone who drives very fast, knows the road well, and has questionable feelings about seatbelts. Modern sailors still know these regions. Round-the-world yacht races often pass through the southern oceans, where the westerlies can provide speed but also extreme risk. Yachts are much stronger and better equipped than vessels of the past, with advanced materials, satellite communication, navigation systems and weather data. But they are still small compared with the ocean. A racing yacht in the Southern Ocean may surf down huge waves, slam into troughs, and endure days of cold, wet motion. The sailors are trained, prepared, and often astonishingly skilled, but the environment remains severe. Technology changes the odds. It does not cancel the sea. The names can also be misleading because the strongest winds are not always neatly arranged by latitude. Weather is not a staircase where every 10 degrees south simply adds one level of chaos. Storm tracks, pressure systems, sea ice, temperature gradients, and seasonal shifts all matter. Sometimes the 40s may be ferocious, sometimes the 50s may be calmer than expected, sometimes the 60s may be complicated more by ice and remoteness than by raw wind speed alone. The names are broad descriptions, not guarantees. The Southern Ocean does not perform on schedule, which is frankly inconsiderate but meteorologically normal. Still, the pattern is real enough. Move south through the southern hemisphere, and the land gives way to ocean. The winds gain more freedom. The storms become part of a vast circulating belt. The sea state grows more serious. By the time you reach the edge of Antarctica, the world feels different from the one most humans inhabit. There are few trees, few buildings, few signs of ordinary life. Instead, there is wind over water, water over depth, and ice moving according to forces that do not need our approval. One of the remarkable things about these wind belts is that they have shaped not just navigation, but culture. They appear in sea stories, expedition accounts, sailing lore, and the language of adventure. To say a ship has entered the Roaring Forties is to suggest a threshold has been crossed. There is the world of ordinary sea travel, and then there is the southern oceanic world, where the air is stronger and the map feels emptier. These names carry the accumulated experience of generations. They are shorthand for risk, speed, endurance, and discomfort. Especially discomfort. Never underestimate how much maritime history has been influenced by people being extremely wet and tired. Bird life in these latitudes seems to understand the wind better than we do. Albatrosses and other seabirds use the strong winds with extraordinary skill. An albatross can glide for long distances using a flight technique called dynamic soaring, gaining energy from differences in wind speed above the waves. While humans brace against the gale and tighten every strap they own, the albatross rides the air with calm efficiency. It is one of the Southern Ocean's quiet insults to human pride. We build ships, forecast systems, and waterproof gear. The bird simply tilts a wing and crosses a storm as if late for lunch. The sea surface below tells a rougher story. In these wind belts, waves are not only high, but often long and powerful. A long Southern Ocean swell can travel across enormous distances, lifting ships in slow, heavy motion. When local wind adds steepness, the sea becomes more aggressive. Breaking waves can crash over decks and superstructures. Even large vessels can be forced to slow down or change course. For smaller boats, survival depends on preparation, design, and seamanship. Every hatch, line, mast fitting, and piece of equipment matters. The Southern Ocean has a way of finding weak points, which is useful in engineering terms, but rather stressful in the moment. The cold makes the wind feel sharper. Wind speed alone does not tell the whole story. A strong wind in warm air is tiring. A strong wind in cold spray can become dangerous. Heat loss increases. Hands lose dexterity. Wet gear becomes heavy. Simple work takes longer. Fatigue builds. On a ship, tired people make mistakes, and the Southern Ocean is not known for forgiving mistakes generously. This is why crews prepare obsessively. They secure gear, check systems, plan watches, monitor weather, and keep routines. Routine may sound boring, but in dangerous places, boring routines are often what keep people alive. These wind belts also influence ocean mixing and climate. The same westerlies that made sailors nervous help drive upwelling in the Southern Ocean. Deep waters can be brought toward the surface, where they interact with the atmosphere and support biological productivity. The winds help connect surface processes with deeper circulation. They are not just a hazard for ships, they are part of how the planet moves heat, carbon, and nutrients. It is a strange thing to realise that winds famous for tearing sails and building waves are also involved in feeding marine ecosystems and regulating climate. The Southern Ocean rarely does only one thing at a time, and that is why these names belong in the larger story of the world's most dangerous ocean. The Roaring Forties, Furious 50s, and Screaming 60s are not decorative phrases. They are a map of exposure. They mark the latitudes where the atmosphere has room to move, where storms circle with fewer barriers, where the ocean responds with some of the largest and most persistent seas on Earth. They remind us that danger in the Southern Ocean is not only found in icebergs or shipwrecks. It begins in the air itself, in the huge invisible movement of wind around the bottom of the planet. Imagine descending through those latitudes on a ship. At first, the change may be gradual. The sea grows longer, the air cools, the horizon seems wider, then the wind becomes steadier, stronger, less interrupted. The ship begins to move differently. Doors must be latched, cups need attention. People start walking with one hand ready to grab something solid. Farther south, the weather becomes more serious. Forecasts are checked more often. The swell builds. The ocean loses the last hints of ordinary friendliness. By the time the ship reaches the 60s, Antarctica is no longer an idea at the bottom of the map. It is near enough to shape the air, the ice, and the water around you. There is no need to imagine these latitudes as constant chaos because the truth is more interesting. They are variable, shifting, and alive with change. Some days the roaring 40s may seem almost restrained. Some crossings of the Drake Passage surprise travellers by being calm enough to earn the nickname Drake Lake. Other times the same passage becomes Drake Shake, which is the sort of nickname that tells you everything you need to know while still sounding faintly ridiculous. Weather has moods, but it also has causes. The Southern Ocean's wind belts are a product of planetary circulation, open ocean, and polar cold, and their danger comes from the scale on which those causes operate. For sailors of the past, the names were warnings learnt the hard way. For modern scientists, they are part of a system that can be measured, modelled, and studied. For the rest of us, listening from somewhere hopefully warmer and less mobile, they offer a way to understand why the Southern Ocean has such a fierce reputation. It is not only the water that is dangerous. It is the wind over the water, the distance the wind travels, the storms it carries, the waves it builds, and the cold world waiting farther south. And once those winds have blown long enough over open sea, the next part of the story rises from the surface itself. The air gives its energy to the water gathers that energy into motion, and motion becomes swell. Sometimes those swells roll for thousands of kilometres. Sometimes they meet other waves and grow steep. Sometimes they rise so high beside a ship that the horizon disappears, and for a moment all anyone can see is a wall of moving water. At sea, a wave is not just water going up and down. It is wind made visible. It is energy passing through the ocean. It is weather leaving fingerprints on the surface, and in the Southern Ocean, those fingerprints can become tall enough to block the horizon. That is the thing about waves down there. They're not always neat, regular, or polite. A person standing on the deck of a ship may look out and see one long swell lifting the whole vessel from behind, while another steeper sea arrives from the side, and wind-driven chop rattles across the top like the ocean has forgotten how many instructions it was given. The ship rises, pauses, falls, rolls, shudders, and climbs again. Sometimes the water is beneath you, sometimes it seems beside you, and sometimes, for a few uncomfortable seconds, it looks as though it is above you, which is not where most people prefer their ocean to be. The Southern Ocean is famous for waves because it has the ingredients waves need: strong wind, long duration, and enormous fetch. We have met fetch already, but it is worth inviting it back into the room, preferably after checking that it has wiped its feet. Fetch is the distance over water that wind can blow in one direction without being stopped by land. The longer the fetch, the more time the wind has to transfer energy into the sea. A light wind over a small pond makes ripples. A strong wind over thousands of kilometres of open ocean can build waves that make ships feel very small and make even experienced sailors become unusually interested in weather updates. Around Antarctica, the wind can travel with fewer interruptions than almost anywhere else on Earth. There are no large continents sitting in the way at those latitudes. The westerly winds sweep around the planet, crossing open water again and again. Storm systems move through. Low pressure deepens, gusts strengthen. The surface darkens and roughens. Small waves become larger waves, and larger waves organise into swell. The Southern Ocean gives the atmosphere enough space to work on the sea for a long time, and the sea responds. It is helpful to separate two ideas that often get mixed together: wind waves and swell. Wind waves are the waves being made by the local wind at that moment. They're often shorter, steeper, and messier. Swell is older. It has travelled away from the storm or wind field that created it. Swell can move across vast distances, sometimes for thousands of kilometres, carrying energy from one part of the ocean to another. In the Southern Ocean, a ship can meet both at once. The local wind may be raising one pattern of waves while long swell from a distant storm rolls in from somewhere else. That is when the surface can become confused. Not confused in the charming way of someone looking for their glasses while wearing them, but confused in the sense that the ship is no longer moving in one easy rhythm. This is one reason Southern Ocean waves are so hard to describe from numbers alone. A forecast might say that the significant wave height is 7 metres, or 10 metres, or more. That is useful information, but it does not tell the full story. Significant wave height is not the height of every wave. It is generally the average height of the highest third of waves in a given period. That means some waves will be smaller, some will be around that height, and some will be larger. A sea with a significant wave height of 10 metres can produce individual waves noticeably higher than 10 metres. This is why the word average should be handled carefully at sea. An average wave does not flood the deck. The larger individual wave that arrives while everyone is trying to eat dinner might. The World Meteorological Organization lists a buoy-measured world record significant wave height of 19 metres in the North Atlantic, which is already a difficult number to picture. 19 metres is taller than many buildings. It is about the height of a 6-storey structure, depending on the building. But remember, that is significant wave height, not necessarily the tallest individual wave in that sea. When the highest third of the waves average 19 metres, the largest waves around may be even bigger. At that point, the ocean is no longer scenery. It is architecture, moving architecture, badly lit and full of salt. The Southern Ocean has produced its own giant measurements. In 2018, a wave of 23.4 metres was recorded at the Campbell Buoy south of New Zealand, a region exposed to Southern Ocean swell and storms. That's about 77 feet. If you stood next to a wave that tall, which is not recommended unless you have made some very unusual life choices, it would rise higher than a 7-storey building. But even saying that does not quite capture it, because a building stands still. A wave moves. A building does not lean over, break, throw spray into the air, and arrive with thousands of tons of water behind it. A building also rarely follows you. A wave can. This is why the phrase, waves taller than buildings, can be true and still not enough. Height is only part of danger. A long, smooth swell may be huge but manageable for a large ship if it is spaced out and moving in a predictable direction. The vessel climbs one side, crosses the crest, and descends the other. Unpleasant, yes. Dramatic, certainly. But not necessarily catastrophic. A shorter, steeper wave can be more dangerous even if it is not as tall, because it can break violently. It can slam into a ship instead of lifting it. It can throw water onto the deck, smash windows, bend metal, damage equipment, and knock people off their feet. The shape of the wave matters. The spacing matters. The direction matters. The speed matters. The mood, although not a scientific term, also seems relevant. To understand why waves break, imagine the wave becoming too steep for its own structure. As wind continues to feed energy into the sea, waves grow taller and steeper. Eventually the crest can move faster than the base, and the wave topples forward. In shallow water near shore, waves often break because the bottom slows them down. In the open ocean, waves can break because they become unstable in strong winds. Whitecaps form. Spray tears from the crests. In extreme storms, larger breaking waves can strike ships with tremendous force. A wave does not need to be the tallest ever measured to be dangerous. It only needs to be steep, breaking, and in the wrong place at the wrong time. The Southern Ocean encourages steep and complicated seas because storms can be large, fast-moving and frequent. A low-pressure system may generate powerful waves over a wide area. As that storm moves eastward, it leaves swell travelling outward. Then another system may develop behind it. Local winds can blow against or across existing swell. The Antarctic circumpolar current moves through the same region. Underwater ridges and changes in depth can also affect how energy moves. The result is often not one perfect wave train, but several overlapping systems. To a passenger, that means the ship may roll one way, pitch another, and then be struck by a wave that appears to have skipped the briefing. For sailors, these waves change everything. They affect course, speed, sleep, cooking, maintenance, safety, and decision-making. A ship may turn to meet waves at a safer angle. It may slow down to reduce slamming. Crew may secure hatches, lash equipment, and stay clipped in on deck. Heavy weather is exhausting because the body never fully rests. Even lying down requires effort when the world is moving beneath you. Muscles tense automatically. The mind listens for unusual sounds. A bang, a crack, a change in engine note, a new vibration. At sea, noises are messages, and in the Southern Ocean, people learn to pay attention. A large vessel can look invincible from the dock. Steel hull, powerful engines, high bridge, radar, satellite systems, safety equipment, and the general confidence of something that weighs thousands of tons. But in Southern Ocean waves, even large vessels can look small. A ship climbing a big swell may have its bow lifted high, then drop into the trough with a deep impact. Water can sweep across the deck in a solid sheet. Containers, cranes, scientific gear, small boats, railings, ladders, and doors all become things that must survive repeated force. The ocean tests every connection: bolts, welds, ropes, hinges, seals. If something is loose, the sea will attempt to remove it. Not out of malice, out of physics, which is often worse because it cannot be reasoned with. For smaller vessels, the challenge is more intimate. A yacht in the Southern Ocean is not merely crossing water, it is living inside motion. Everything must be arranged so it can continue working while tilted, wet, cold, and shaken. Sailors must manage sails in high wind, avoid being rolled, prevent gear failure, and maintain enough rest to think clearly. A wave breaking over a small boat can fill the cockpit, damage equipment, or injure crew. A knockdown, where the boat is pushed onto its side or farther, is one of the great fears. A well-designed offshore yacht may recover, but the experience is not one anyone describes as soothing unless they are trying very hard to impress someone. And yet, people go there. Racing sailors, expedition crews, researchers, naval vessels, fishing boats, supply ships, and tourist vessels all enter parts of the Southern Ocean for different reasons. They do not go because it is easy. They go because it matters, or because the route demands it, or because Antarctica draws people with a force that is difficult to explain but easy to recognize. The waves become part of the price of entering that world. You do not visit the Southern Ocean and ask it to behave like a lake. You prepare for it as it is. There is a long history of sailors describing waves in the southern latitudes in almost unbelievable terms. Before modern instruments, wave height was often estimated by eye, which is difficult even in calm conditions and nearly impossible when your ship is moving like a cupboard falling downstairs. A wave seen from a deck can look enormous because the observer is rising and falling too. A trough can make the next crest appear taller. Darkness, fear, and spray do not improve measurement accuracy, so old accounts must be read carefully. Sailors were not necessarily exaggerating, but they were observing from a moving platform in dangerous conditions. Still, the repeated reports of mountainous seas were not fantasy. Modern instruments have confirmed that the Southern Ocean can produce truly huge waves. Today, scientists use buoys, satellites, radar, pressure sensors, autonomous vehicles, and ship observations to study wave height. Buoys can measure heave, the up and down motion of the water surface. Satellites can estimate wave height over broad areas. Autonomous surface vehicles can travel into places too difficult or expensive for crewed ships to monitor continuously. These tools help improve wave forecasts and climate models. They also remind us how much of the Southern Ocean remains hard to observe. A satellite can see a pattern, a buoy can record a point, a ship can report a crossing. But the ocean is vast, and the worst conditions often happen when no one is waiting with a measuring tape, which is probably for the best. One interesting thing about Southern Ocean waves is that they do not always stay in the Southern Ocean. Swell generated by southern storms can travel northward into other ocean basins. A storm near Antarctica can send energy across the sea for days. By the time that swell reaches a distant coast, the weather that made it may be long gone. Surfers, coastal engineers, and marine forecasters understand this well. Waves arriving at a shore are not always made by local wind. They may be messages from storms far away. In that sense, the Southern Ocean speaks across distance, sending long pulses through the global ocean. It is a very dramatic pen pal. The energy in waves also matters for climate and ice. Waves can break up sea ice at the edge of the ice pack. They can influence how far wave energy penetrates into ice-covered waters. They mix the upper ocean. They affect air-sea exchange by roughening the surface and creating spray and bubbles. This means waves are not just hazards for ships. They are part of how the ocean interacts with the atmosphere and cryosphere. A wave that looks like a problem for navigation may also be part of a process involving heat, gas, salt, ice, and energy. The Southern Ocean is very good at making one thing do several jobs, which is efficient but not always considerate. Rogue waves deserve a careful mention here because they are often surrounded by stories. For a long time, sailors reported enormous sudden waves that seemed out of proportion to the surrounding sea. Some people treated these stories with doubt, as sea tales made larger in the telling. But modern measurements have shown that rogue waves do occur. They are commonly defined as waves more than twice the significant wave height. That does not mean they come from nowhere in a magical sense. They arise from physical processes, including the interaction of waves, currents, and wind, but the exact details can be complex. In the Southern Ocean, where seas can already be high and complicated, the possibility of an unusually large wave adds another layer of concern. Imagine a sea where the significant wave height is 8 meters. That is already a serious sea. A rogue wave in that situation, by the usual definition, would be over 16 meters. Now imagine meeting it in darkness, with wind, noise, spray, and the ship already moving heavily. This is why sailors respect not only the forecast height, but the range of possibilities around it. The ocean is not a machine producing identical waves one after another. It is a field of interacting energy. Most waves may fall within a pattern, but occasionally one wave stands out, and that one may be the wave everyone remembers. There is also the problem of wave period, which is the time between wave crests. A long period swell can carry huge energy. The waves may look less steep but move powerfully. A short period sea can be steep and chaotic, with crests closer together. Ships respond differently to different wave periods. Every vessel has natural motions. Under certain conditions, waves can match or worsen those motions, increasing rolling or pitching. This is why marine forecasts include not just wave height, but period and direction. A number alone is never enough. The sea is a three-dimensional problem arriving repeatedly. From the bridge of a ship, a big Southern Ocean sea changes what the world looks like. When the vessel is in a trough, the view may be mostly water. The horizon disappears behind a dark wall. Then the bow climbs, the ship rises, and suddenly the horizon returns, wide and grey. For a moment you can see across the crests, then down again. The motion repeats, sometimes for days. The mind gets used to it, then gets tired of it, then gets used to being tired of it. People move carefully, meals become simple, sleep comes in fragments. Even conversation changes because everyone is listening to the ship and the sea. On deck, the scale is physical. A breaking wave can hit with a force that feels less like water and more like a moving wall. Spray can sting exposed skin. Cold water can run under collars and into gloves. Footing is uncertain. Safety lines matter. Handrails matter. Doors matter. The ordinary idea of water as soft disappears quickly. Water is soft in a glass. In a Southern Ocean storm, water has mass, speed and intention, or at least it produces the strong impression of intention while remaining technically innocent. The largest waves are often born when strong winds blow over a large area for a long time. A compact storm may produce rough seas locally, but a broad storm with sustained winds over a long fetch can build swell with great energy. In the Southern Ocean, storms can have room to become broad. The circumpolar nature of the ocean means wave systems can travel around and across large stretches without being stopped by land. It is not one storm alone, but the repeating pattern of storms and winds, season after season, year after year, that gives the region its wave climate. Wave climate is the long-term pattern of waves in a region. Just as a place can have a rainy climate or a dry climate, an ocean region can have a wave climate shaped by typical winds, storms, currents, and geography. The Southern Ocean's wave climate is among the most energetic on Earth. That means high average wave energy, frequent storms, and strong swell systems. Not every day is extreme. There are calm periods. The sea can flatten, light can break through, and the surface can look almost friendly. But the background expectation is different from most oceans. In the Southern Ocean, calm can feel temporary. Roughness feels like the default setting waiting to return. For Antarctic travel, waves often provide the first real test. Many people heading to the Antarctic Peninsula cross the Drake Passage, where the Pacific and Atlantic sectors meet between South America and Antarctica. The passage is famous for rough seas, though it can also be surprisingly calm. Travellers speak of the Drake Shake and the Drake Lake, which is a tidy way of saying the crossing may be either memorable or suspiciously gentle. Large swells can roll through the passage and storms can make conditions severe. A person may board a ship excited about penguins and icebergs, then spend 2 days learning a very personal lesson about inner ear fluid. The Southern Ocean has many educational methods, but the waves are not only an obstacle to tourism or shipping, they also shape the coast of Antarctica and the ice around it. Where waves reach ice shelves or sea ice edges, they can contribute to breakup in some conditions. Wave action can flex ice. It can widen cracks. It can break flows into smaller pieces. The relationship between waves and ice is complex because ice can also dampen waves and prevent them from travelling farther. Scientists study this carefully because changing sea ice conditions may alter how waves move into polar regions. Less ice cover can allow waves to travel farther south, which may then affect remaining ice. As usual, the Southern Ocean refuses to be a simple system. There is a strange comfort in the fact that waves, for all their danger, follow rules. They can be modelled, measured and forecast. Their behaviour emerges from wind, gravity, rotation, water depth, currents and energy transfer. We may not predict every individual wave perfectly, but we understand the processes well enough to improve safety and planning. A forecast showing a large swell is not just a warning. It is the result of physics turned into useful information. Somewhere, data from satellites, buoys, ships, and atmospheric models has been gathered and processed, so that a crew can decide whether to continue, slow down, change course, or secure equipment. Science does not make the waves smaller, but it can help people meet them with fewer surprises. And perhaps that is one of the quiet themes of the Southern Ocean. Humans are not in control there, but we are not helpless either. We learn, we measure, we build stronger ships, we design better survival systems, we train crews, we improve forecasts, we send autonomous instruments into storms. We study wave-ice interaction, storm tracks, and ocean energy. Every piece of knowledge is a small light in a large, grey place. Not a light that conquers the ocean, more like a lamp on the chart table, helping us understand where we are. Still, no amount of understanding removes the feeling of seeing a truly large wave approach. Numbers become secondary. The body recognizes scale before the mind finishes explaining it. A crest rises. The ship turns or climbs. The water roars past. Spray fills the air. Then the wave is gone, and another is already forming behind it. The ocean does not pause for admiration. It keeps moving, because that is what the energy in it must do. So, when we say the Southern Ocean has waves taller than buildings, we're speaking about more than height. We're speaking about a system where wind has space, storms have strength, swell has distance, and water has time to gather energy. We're speaking about waves that can travel far from their birthplace. Waves that can batter ships, break ice, shape forecasts, and remind every person at sea that the surface of the ocean is never merely a surface. It is the moving boundary between atmosphere and deep water, between weather and current, between human plans and planetary scale. And as these waves move through the southern latitudes, they do not move through empty water. They move through cold. They move through fog, snow, and freezing spray. They move past floating ice that may be small enough to miss, or large enough to appear on satellite images. A ship that survives the wind and rides the swell must still watch for the pale shapes ahead, because in the Southern Ocean the danger is not only what rises from below the hull, but what drifts silently across its path. And in the Southern Ocean, the water is only part of the problem. A wave can rise, strike, and pass. A storm can move through, leaving behind a tired ship and a crew suddenly believe very strongly in soup. But ice is different. Ice waits. Ice drifts. Ice changes shape. Ice can be beautiful enough to make people stop speaking for a moment, and dangerous enough to make them start speaking very quickly again. To understand why ice makes the Southern Ocean so difficult, we need to begin with a simple distinction. There is sea ice, and there are icebergs. They are both frozen water, yes, but they are not the same thing. Sea ice forms when the surface of the ocean freezes. It is made from seawater, although much of the salt is pushed out as the ice forms. It can spread across huge areas around Antarctica during winter, then retreat again in summer. Icebergs, on the other hand, are pieces of land ice. They break away from glaciers or ice shelves, falling or sliding into the ocean as floating chunks of Antarctica itself. Sea ice is the ocean freezing. Icebergs are the continent breaking off and going for a very slow swim. That difference matters. Sea ice is usually thinner than icebergs, although it can still be thick enough to stop or damage a vessel. It forms in sheets, plates, ridges, flues, and broken fields. It can cover wide areas and create a moving maze. Icebergs can be far larger and deeper because they come from the thick ice resting on land or attached to the edge of the continent. A large iceberg may tower above the sea like a white cliff, but most of its mass is below the surface. This is the familiar iceberg fact everyone knows, and yet it remains unsettling every time. What you see is only the polite introduction. The larger, heavier, ship-scraping part is hidden underwater, like an enormous frozen secret. The Southern Ocean contains both kinds of ice, and together they change the rules of travel. A ship can be built to handle waves. It can be strengthened for polar waters. It can carry radar, sonar, satellite navigation, ice charts, and experienced officers on the bridge. But ice still requires caution. It does not move like a coastline. It does not stay fixed like a rock on a chart. It drifts with wind and current. It breaks apart. It rotates. It melts unevenly. It carves smaller pieces. It appears in fog, snow, darkness, and rough water. Sometimes it is obvious from far away. Sometimes it is not. And the smaller pieces can be the most treacherous because they may not look impressive but can still damage a hull. There are names for some of these smaller pieces. A growler is a small iceberg or chunk of ice, often low in the water, sometimes only a little larger than a car or piano. A bergy bit is bigger than a growler but smaller than a proper iceberg. These names sound almost charming, as if someone were describing snacks at a polar picnic. But at sea they are serious hazards. A growler can be hard to see in rough waves because it may be dark, rounded and wet, with only a small part showing above the water. Radar may not always detect it clearly, especially if conditions are messy. And unlike a wave, which lifts and passes, a chunk of ice is solid. Ships do not enjoy solid surprises. In the open Southern Ocean, icebergs can drift far from where they were born. They are carried by currents and pushed by winds. Large icebergs may survive for years. Some become famous in the way only giant drifting blocks of ice can become famous, which is to say mostly among scientists, satellite watchers, and people who enjoy maps. Iceberger 23A is a good example. It calved from Antarctica's Filchner ice shelf in 1986, then stayed grounded on the seabed in the Weddell Sea for more than 30 years. Imagine breaking away from a continent and then immediately getting stuck for decades. It is not exactly a dramatic escape, but icebergs work on their own schedule. Eventually, a 2-3 oil began moving, drifting with the currents of the Southern Ocean. It was enormous, often described as more than twice the size of Greater London, and it became one of the most watched icebergs in the world. Satellite images followed it as it moved northward. In 2025, a British Antarctic survey reported that it had grounded near South Georgia, about 90 kilometres from land. That is a long journey from the Antarctic ice shelf where it began. It is also a reminder that icebergs are not just local hazards near the Antarctic coast. A large berg can travel into sub-Antarctic waters, enter shipping and fishing regions, affect wildlife access, and slowly release fresh water and material into the ocean as it melts. A big iceberg can look almost still, but it is part of a moving system. Currents push it. Wind pushes the exposed part above water. Waves strike it. Warmer water eats away at its edges and underside. Cracks spread. Caves form. Pieces break off. Sometimes an iceberg rolls because melting changes its balance. That can be dangerous nearby because a rolling iceberg can move a large amount of water and throw smaller pieces into the sea. It is not a quiet sculpture. It is a weakening structure floating in rough water. Beautiful, yes. Stable, not always. Sea ice creates a different kind of challenge. It is not one object to avoid. It is a landscape that moves. Around Antarctica, sea ice expands during the dark, cold months and contracts during the brighter summer months. At its winter maximum, it can cover a huge ring of ocean around the continent. In summer, much of it melts back, opening water routes that were closed or difficult months before. This seasonal change shapes navigation, ecosystems, and research planning. Ships heading south pay close attention to ice conditions because the location, concentration, and thickness of sea ice can determine where they can go. Sea ice is often described by concentration, meaning how much of a given area is covered by ice. A region may be open water, scattered ice, broken ice, close pack, or nearly solid cover. The difference matters. A ship may move through scattered flows with care. It may struggle through heavy pack ice. It may have to stop entirely if the ice becomes too thick or compressed. Wind can push flows together, closing gaps and trapping vessels. Current can move ice into a route that was open before. A passage may look possible on a chart, then become blocked by the time a ship arrives, because the ice did not feel bound by anyone's travel plans. This is why ice navigation is a skill of its own. It is not simply steering around white objects. Crews read ice charts, satellite imagery, weather forecasts, and local conditions. They watch for leads, which are openings or channels in the ice. They look for changes in colour and texture. They judge whether flows are loose enough to pass through or packed tightly enough to become dangerous. In heavy ice, pressure can build as flows are pushed together. Ice can squeeze against a hull. It can trap a ship, push it sideways, or damage propellers and rudders. An ice-strengthened vessel can handle more than an ordinary ship But no vessel is immune to poor judgment. The ice does not care how expensive the ship was. The Southern Ocean's frozen maze becomes even more difficult because of visibility. In clear weather, ice can be breathtaking. Sunlight turns snow and ice into bright white, pale blue, and deep turquoise. Icebergs can look carved, arched, layered, and impossibly clean. Some have flat tops like tables. Others have spires, ridges, caves, and overhanging shelves. They can resemble castles, cliffs, frozen ships, or very large deserts made by someone with no sense of portion control. But the same ice in fog, snow, or darkness is a different matter. White ice in white weather can vanish. Low ice in rough water can hide behind waves. A berg in twilight may appear as a faint change in shade, and by the time it becomes clear, everyone on the bridge may suddenly become extremely focused. There is a word often used in polar regions, ice blink. It describes a pale brightness seen on the underside of clouds, caused by light reflecting from ice below. Before satellites and modern instruments, signs like this helped navigators infer where ice might be. Open water can produce a darker reflection, sometimes called water sky. These old observations remind us that polar navigation has always depended on careful attention. The environment gives clues, but it does not give them loudly. A change in light, a shift in swell, a line on the horizon, a patch of birds, a temperature drop. In the Southern Ocean, noticing small details can matter. Sea ice also changes the waves. Open water allows waves to grow and travel. Sea ice can dampen wave energy, breaking up swell and quieting the surface within the pack. This can sound helpful, and sometimes it is. A ship inside ice may be protected from the full force of open ocean swell. But that protection comes with its own risks. Ice can press, close, and trap. At the edge of the ice pack in the marginal ice zone, waves and ice interact in complicated ways. Waves break floes apart. Floes rub and collide. Broken ice can form a rough field of pieces that are difficult to pass through. It is not simply open water or solid ice. It is a shifting boundary, and shifting boundaries are rarely easy places to work. For wildlife, however, sea ice is not just an obstacle, it is habitat. Antarctic krill can feed on algae growing under the ice. Seals use ice for resting, breeding, or access to feeding areas. Penguins depend on certain ice conditions depending on species and location. The timing and extent of sea ice affect food webs. Too much ice in some places can make travel difficult for animals. Too little ice in other places can reduce habitat or affect breeding success. The frozen maze that challenges ships is also part of the living structure of the Southern Ocean. This is one reason recent changes in Antarctic sea ice have drawn so much scientific attention. For many years, Antarctic sea ice did not decline in the same clear way as Arctic sea ice. It showed strong regional differences and large year-to-year variation. Then, in recent years, scientists observed very low Antarctic sea ice extents, including record or near-record low minimums. The details are still being studied because Antarctic sea ice is influenced by winds, ocean temperature, salinity, storms, and regional patterns around a vast continent. But the concern is serious. Sea ice affects climate, ecosystems, ocean circulation, and the exchange of heat between the sea and atmosphere. Sea ice is highly reflective compared with dark open water. This is called albedo. Ice reflects much of the sunlight that hits it, while open ocean absorbs more. When sea ice is reduced, more dark water can be exposed, allowing the ocean to take in more solar energy. That can lead to further warming in the surface ocean, depending on the season and conditions. The basic idea is simple enough to test with clothing on a sunny day. Wear a white shirt and then a black one. The black one feels warmer because it absorbs more light. The ocean is not a shirt, thankfully, but the principle of reflectivity still matters. When sea ice forms, it also affects salt. As seawater freezes, much of the salt is rejected into the water below, making that water saltier and denser. Dense water can sink, contributing in some regions to the formation of deep and bottom waters. When sea ice melts, it adds fresher water to the surface, which can make the upper ocean more layered and influence mixing. These processes are not just local details. They connect to the larger circulation of the global ocean. Once again, the Southern Ocean takes something that looks like scenery and turns it into planetary machinery. Icebergs also contribute fresh water as they melt. They can carry iron and other nutrients depending on their origin and composition, and their meltwater can influence local ecosystems. But not all icebergs have the same effect. Recent research has shown that different megabergs can affect the waters around them in different ways. One iceberg may release nutrients that encourage biological activity, while another may have little measurable impact at the time it is sampled. This is a useful warning against thinking of all ice as the same. Icebergs have histories. They come from different parts of Antarctica. They carry different materials. They melt in different waters. Even frozen things have biographies, which is both scientifically true and slightly unfair to those of us who thought ice was going to be simple. For ships, though, the immediate concern remains collision and entrapment. Modern vessels use satellite data, radar, ice services, and careful routing to reduce risk. Large icebergs are usually tracked, especially the famous ones, but smaller fragments are harder. A big iceberg breaking apart can create fields of smaller ice. These fragments may spread over wide areas. A vessel travelling through them must slow down, increase watchkeeping, and sometimes change course. Speed is dangerous in ice because it reduces reaction time and increases impact force. In open water, speed can be progress. In ice, speed can become arrogance. Night makes everything harder. So does fog. So does snow. So does rough sea. The Southern Ocean can offer all of these together because apparently it believes in package deals. Imagine standing watch in poor visibility, with cold spray on the windows, radar clutter on the screen, the ship rolling, and ice reports suggesting bergy bits nearby. The work becomes tense and careful. It is not dramatic in the movie sense. There may be no shouting. Often the most serious work at sea is quiet. People watch, compare, calculate, adjust, and wait. A small course change made early can prevent a dangerous close approach later. Good seamanship often looks boring, which is one of its finest qualities. Ice can also threaten scientific work. Researchers may need to reach certain areas to deploy instruments, sample water, study wildlife, or service equipment. Sea ice can block access. Icebergs can make routes unsafe. Conditions can change after a ship has entered an area, creating pressure to leave before ice closes in. Planning Antarctic research means planning around ice, but planning around ice is like planning around a slow crowd that may rearrange itself overnight. It requires flexibility, patience, and the ability to accept that sometimes the ocean says no. There is also the sound of ice, something that does not always appear in documentaries because cameras are too busy showing the views. Sea ice can grind, scrape, crack, and bump against the hull. Icebergs can carve with sharp cracks and low thunder. Brash ice, the small broken pieces, can hiss and clatter in the water. A ship moving through ice may produce a steady scraping sound along the hull, a sound that reminds everyone on board that the environment is touching the vessel directly. In open water, danger can feel separate, out there in the waves. In ice, the danger may be pressing against the sides. The beauty of the frozen maze is part of its power. It does not look like a place of simple threat. It can look calm. A field of sea ice under low sunlight can seem peaceful, almost still. Penguins may stand on floes. Seals may rest with the casual confidence of animals that have never had to pay rent. Snow may soften the edges of everything. The water between floes may reflect the sky. Then the wind shifts, the ice begins to move, and the same scene becomes difficult. Beauty is not safety. The Southern Ocean teaches that lesson often. Icebergs especially carry that contradiction. They are among the most beautiful hazards on Earth. Their blue colour comes from the way dense old ice absorbs longer wavelengths of light and scatters shorter blue wavelengths. Cracks, melt channels, and compressed layers create patterns. Some icebergs carry dark lines of rock dust or sediment. Others have smooth sides carved by waves. When they melt, they may form arches and caves, which can collapse without warning. A photographer may see shape and colour. A navigator sees drift, draft, and distance. Both are correct. The iceberg is stunning, and it is also in the way. The frozen maze is not fixed in time. It changes by hour, season, and year. A route open in January may be blocked in December. A bay clear one week may fill with ice the next. A large iceberg may remain grounded for decades, then suddenly start moving. Sea ice may form later, melt earlier, expand unusually, or retreat sharply depending on conditions. This changeability is part of why the Southern Ocean remains difficult, even in the age of satellites. We can see more than ever before, but seeing is not the same as controlling. The ice continues to drift according to wind, current, temperature, and chance. For the crews who travel there, ice creates a different rhythm from waves. Waves demand balance and endurance. Ice demands patience and attention. You slow down, you watch, you pick a route, you avoid being trapped, you respect what you cannot see below the surface. You remember that a white field ahead may be thin and open, or thick and closing. You treat every pale shape as important until proven otherwise. It is a cautious way of moving through the world, and perhaps not a bad lesson beyond the ocean. So the Southern Ocean's frozen maze is more than a collection of hazards. It is a seasonal skin, a wildlife platform, a climate actor, a navigation challenge, and a record of Antarctica breaking, freezing, melting, and drifting at the edge of the planet. Sea ice forms from the ocean and spreads outward. Icebergs break from the land and wander north. Together they create a place where routes open and close, where beauty hides weight, where the surface can be quiet but never simple. A ship leaving the ice behind may feel relief as the water opens again, but open water brings back the waves. The wind returns without the ice to soften it. The swell begins to lift the hull. Behind the ship, pale shapes drift in the grey distance. Ahead, the southern storm tracks continue their long circuit around the world, carrying with them the older human stories of vessels that crossed these waters, some successfully, some barely, and some not at all. A ship in the Southern Ocean is never just travelling across water. It is entering a long argument between human planning and planetary force. The charts may be accurate, the engine well maintained, the crew experienced, and the forecast studied carefully, but once a vessel is far down in those latitudes, everything becomes a negotiation. Wind, waves, ice, distance, cold, fatigue, and timing all have something to say. And the ocean, as you may have noticed by now, does not usually wait politely for its turn. For centuries, sailors looked south with a mixture of fear and opportunity. The Southern Ocean was dangerous, yes, but it was also useful. In the age of sail, wind was not just weather. Wind was fuel. A sailing ship depended on it entirely. Too little wind could trap a vessel in dull, rolling helplessness for days. Too much wind could tear sails, break masts, flood decks, and scatter cargo across a hold like the ship had tried to make soup out of furniture. The great westerlies of the southern latitudes offered speed, and speed was valuable, so ships went south. They went looking for the roaring forties because those winds could push them eastward across the world. A vessel sailing from Europe toward Australia, New Zealand, or the Far East could use the southern winds to shorten the passage. Merchant ships, clippers, sealers, whalers, explorers, and later scientific expeditions all entered these waters for reasons that made sense at the time. Money, discovery, trade, food, maps, ambition, sometimes duty, sometimes the particular human habit of seeing a dangerous blank space and thinking, well, someone ought to go there. The clipper ships are among the most famous examples. Long, narrow, fast and built for speed, they used the winds of the southern latitudes like a road. But it was a road that moved, shouted, and occasionally threw solid water over the deck. These ships carried goods across enormous distances, and their captains were often judged by the speed of their voyages. A fast passage could bring profit and reputation. A slow passage could lose money. The pressure to drive a ship hard was real, and in the Southern Ocean, driving hard could mean carrying sail in rough conditions, pushing through heavy seas, and trusting that the vessel, the rigging, and the crew could endure. There is a strange tension in that. The very thing that made the Southern Ocean useful also made it terrifying. A steady, strong wind from behind could send a ship flying eastward. But if that wind rose too far, or shifted badly, or arrived with a deepening storm, the gift became a threat. Sailors had to reduce sail before the ship became overpowered. They had to climb rigging in cold wind, handle heavy canvas, secure lines, and work while the deck heaved beneath them. Modern people complain when a fitted sheet is hard to fold. Imagine dealing with wet canvas high above a rolling deck in the furious 50s. The fitted sheet suddenly seems like a small domestic misunderstanding. Old sailing vessels were strong in their way, but they were vulnerable. Wood worked under strain. Iron fastenings loosened. Sails ripped. Masts cracked. Pumps failed. Cargo shifted. A leak that might be manageable in calm seas became far more serious when every wave struck the hull with force. And because voyages were long, damage could accumulate. A ship might survive one gale, then another, each one leaving it a little weaker. The Southern Ocean did not always destroy ships in a single dramatic moment. Sometimes it wore them down. That is one reason the phrase "graveyard of storms" feels fitting, even if it is not a neat official label printed on a map. The Southern Ocean is not a cemetery in the ordinary sense. There are no gates, no stones, no paths between quiet trees. But storms gather there, travel there, and leave behind stories. Some stories ended in ports, with crews exhausted but alive, ships repaired, and sailors telling the tale with hands wrapped around something warm. Others ended in wreckage, loss, and empty horizons. The ocean kept few records of its own. Humans had to write them down later, if anyone returned to write at all. Cape Horn became one of the most feared names in maritime history, because ships returning from the Pacific to the Atlantic often had to fight around the southern tip of South America. It was not Antarctica, but it belonged to the same hard southern world of westerly winds, cold water, and heavy seas. A sailing ship trying to round Cape Horn from west to east could use the winds. Trying to round it the other way, against prevailing wind and current, could be brutal. Sailors might spend weeks battling gales, making progress one day and losing it the next. The phrase "rounding the horn" became a mark of experience, something that separated those who had truly met the Southern Oceans from those who had merely read about them from a stable chair. Farther south still, Antarctica waited behind ice and distance. For explorers, the Southern Ocean was the outer wall. Before anyone could cross the ice or study the continent, they had to survive the water around it. Early Antarctic expeditions depended on ships that could withstand ice pressure, storms, and isolation. They sailed into seas where charts were incomplete, weather information limited, and rescue nearly impossible. Every decision mattered: where to anchor, when to leave, how close to enter the pack, whether to wait or retreat. The ocean was not just the route to exploration. It was part of the expedition, part of the danger, and often the first great test. No story captures this better than Ernest Shackleton's endurance. The ship sailed into the Weddell Sea during the Imperial Transantarctic Expedition, became trapped in pack ice, and was eventually crushed. It sank in 1915, leaving Shackleton and his men stranded in one of the harshest environments on Earth. The survival story that followed has become famous for good reason. The crew camped on ice, launched small boats, reached Elephant Island, and Shackleton then made an extraordinary open boat journey to South Georgia to seek help. All of his men survived. That fact still feels almost impossible, like a sentence that should come with a raised eyebrow from history. The Endurance story is often told as a triumph of leadership, courage, and persistence, and it is. But it is also a reminder that in the Southern Ocean, a ship can be defeated by more than waves. Ice can be stronger than timber. Pressure can build slowly until the hull gives way. The vessel may be beautifully built, well crewed, and carefully handled, but the environment can still exceed it. When pack ice grips a ship, the danger is not always sudden impact. It can be compression, grinding, twisting, and relentless force. The ice moves at its own pace, and the ship is simply caught inside it. More than a century later, the wreck of Endurance was found on the floor of the Weddell Sea. The discovery was remarkable not only because of the ship's history, but because the Weddell Sea remains difficult even now. Ice conditions, remoteness, depth, darkness, and cold all make searching there challenging. Modern technology found what earlier generations could only imagine, yet the wreck resting deep below the surface is also a quiet symbol. Human courage can be immense, human technology can be brilliant, but the Southern Ocean keeps its own scale. The age of sail eventually gave way to steam, and then diesel power. Engines changed everything. A powered vessel did not need wind in the same way. It could move through calm, keep a schedule more reliably, and avoid some of the old sailing routes. The opening of canals also changed global shipping. The Suez Canal and Panama Canal altered the routes ships used, reducing the need for many commercial vessels to go far south. The Southern Ocean became less central to everyday trade than it had been during the Great Sailing era. But it did not become safe. It merely became less crowded. Modern ships are stronger, better equipped, and better informed. They have steel hulls, navigation systems, radar, satellite communication, automatic identification systems, emergency beacons, survival suits, enclosed bridges, weather routing, and engines capable of pushing through conditions that would have stopped older vessels. A modern research ship can carry laboratories into polar waters. Icebreakers can open paths through sea ice. Cruise ships can bring visitors to Antarctica. Fishing vessels can work remote southern waters. Military and rescue vessels can operate where earlier sailors would have felt almost completely alone. And yet, the Southern Ocean still demands respect. A modern vessel may have technology, but it is still a physical object in water. It can still lose power. It can still suffer hull damage. It can still be struck by a breaking wave. It can still meet ice in poor visibility. It can still experience mechanical failure far from help. The crew still gets tired. Equipment still breaks at inconvenient times because equipment has a deep spiritual commitment to choosing the worst possible moment. A ship may be modern, but the wave hitting it is not impressed by software updates. This is especially true for smaller vessels. Ocean racing has brought some of the most dramatic modern encounters with the Southern Ocean. Round-the-world races send sailors into the same wind belts that clippers once used, but now in lightweight, high-performance yachts designed for speed. These boats can move astonishingly fast. They can surf down waves, cross oceans at speeds old sailors would have found almost unbelievable, and send back data, video, and messages in real time. But they are still vulnerable. A broken mast, damaged keel, failed rudder, collision with floating debris or capsize can quickly become life-threatening. The 1990s saw several dramatic Southern Ocean rescues that showed both the danger and the reach of modern search and rescue. In 1994, French sailor Isabelle Autissier was rescued after her yacht was dismasted and damaged in severe Southern Ocean conditions. In 1997, during the Vendée Globe, sailors Thierry Dubois and Tony Bullimore triggered distress beacons far south of Australia. Bullimore's yacht capsized, and he survived for days inside the upturned hull before being rescued. These stories are often described as miraculous, and it is easy to see why. But miracles at sea usually involve a great deal of training, coordination, courage, technology, and people willing to go out into dangerous water to bring someone home. Search and rescue in the Southern Ocean is unlike rescue closer to shore. Distance stretches everything. A ship may need days to reach the distress position. Aircraft may be limited by range and weather. The person in trouble may be drifting, injured, cold, or inside a damaged vessel. The rescue vessel itself must enter the same dangerous conditions. A distress beacon can tell rescuers where to go, but it cannot calm the sea when they arrive. It cannot stop the wind, remove the swell, or make a life raft easier to spot among whitecaps. The Southern Ocean turns rescue into endurance. There is something deeply moving about that. The ocean is vast and indifferent, yet human beings still go to help each other in it. A naval ship changes course. A cargo vessel diverts. A fellow racer abandons competition. A helicopter crew lifts off. Rescue coordinators stay awake through the night. People study weather, fuel, drift, and timing. In a place where humans are so small, cooperation becomes one of our strongest tools. The Southern Ocean may not care who survives, but people do. That cooperation is especially important because cold water shortens the clock. In warmer seas, a person in the water may have more time. In Southern Ocean conditions, hypothermia can develop quickly. Survival suits help, life rafts help, emergency beacons help. But exposure remains dangerous, even inside a damaged yacht or life raft. Cold, wet, darkness, fear, and motion can wear a person down. Waiting becomes its own ordeal. The ocean may be loud outside, but inside the mind the waiting can be louder. Commercial and research crews face different risks. A fishing vessel working southern waters may deal with long hours, heavy gear, freezing spray, and dangerous deck operations. A research ship may deploy instruments in rough seas, handle winches and cables, launch small boats, or work near ice. A tourist vessel may carry passengers who are not professional sailors and may be encountering polar conditions for the first time. Each type of ship has its own safety systems and procedures, but the environment is shared. The Southern Ocean does not separate people by job title. It gives everyone the same waves. Ice navigation adds another layer. A ship moving through icy waters must slow down, watch constantly, and plan routes around bergs, growlers, and sea ice. Radar, satellite imagery, and experienced lookouts are essential, but none are perfect. A large iceberg may be easy to see. A low, dark growler in rough seas may not be. At night, in fog or in snow, even modern navigation becomes more demanding. The bridge team must combine instruments with judgment. The old sailor's habit of careful watching has not disappeared. It has simply gained screens. Storms remain the central hazard. A storm at sea is not only wind, it is wind working with waves, pressure, visibility, temperature, and fatigue. In the Southern Ocean, storms can produce long-lasting heavy conditions. A vessel may not be able to outrun the system. It may have to choose the best angle, reduce speed, secure everything, and ride it out. That phrase, ride it out, sounds almost relaxed from land. It is not relaxed. It means hours or days of motion, noise, strain, and vigilance. It means trusting the ship, the crew, and the preparations made before the weather arrived. It means hoping that everything important holds. When a ship is in heavy Southern Ocean weather, ordinary life becomes strange. Eating is difficult. Sleeping is broken. Walking requires timing. Opening a door can be a small battle. The safest path across a room may change with every roll. People wedge themselves into bunks. Cups slide, drawers slam. The ship groans, not in a dramatic, ghostly way, but in the practical way of metal and fittings under load. Outside, the sea rises and falls in grey walls. Inside, the crew maintains routines, because routines are how humans stay functional when the world becomes unstable. This is one of the less romantic truths of seafaring. Survival often depends not on grand speeches, but on small repeated acts done correctly. Clipping on, closing hatches, checking bilges, logging position, watching pressure, resting when possible, eating even when not hungry, keeping hands dry, securing tools, communicating clearly. The Southern Ocean rewards discipline, it punishes carelessness, and it has a special talent for turning small oversights into large problems. Still, people who work there often speak of the place with respect rather than hatred. That is important. Sailors may fear the Southern Ocean, but many also admire it. There is beauty in the long swell, the huge sky, the flight of albatrosses, the first sight of ice, the clean cold air after a storm, the strange light near Antarctica. A dangerous place can also be magnificent. In fact, part of the danger may be that magnificence draws people back. The Southern Ocean is severe, but it is not ugly. It can be breathtaking in the most literal sense, especially if the wind is strong enough. The ocean also creates identity. To have sailed the Southern Ocean is to have crossed a threshold. Sailors remember it. Researchers remember it. Passengers remember it, often with very specific opinions about seasickness. The experience becomes part of how people understand the sea and themselves. It teaches scale. It teaches humility. It teaches the value of preparation and the limits of confidence. A person may leave port with ambition, but after days in southern weather, ambition tends to become more practical. Dry socks, warm food, a steady watch, a safe course. These become excellent goals. The Southern Ocean's long list of ship stories is not only a record of disaster, it is a record of adaptation. Humans learn to build stronger vessels, read weather better, plan routes more carefully, create rescue systems, regulate polar tourism, protect fragile ecosystems, and study the ocean with improved tools. Every storm that damaged a ship, every difficult rescue, every near miss, every hard lesson became part of a wider body of knowledge. The sea remained dangerous, but people became better at meeting it. Even so, the old truth remains. No vessel is larger than the ocean it crosses. A ship can be strong, but the Southern Ocean is vast. A captain can be skilled, but the weather can still become severe. Technology can guide, warn and connect, but it cannot remove the cold or shorten the distance. The graveyard of storms is not a place humans conquered. It is a place humans learn to enter carefully, and sometimes leave gratefully. There is a quiet image worth holding for a moment. A ship moving eastward in the Southern Ocean at night. The bridge lights dim, radar turning, the hull lifting and falling in long swell. Somewhere outside, wind moves across the deck. Far above, clouds race through darkness. Far below, deep water moves in slow currents older than any vessel. The people on board are awake, watching, measuring, adjusting. Small human figures inside a steel shell, crossing one of the hardest oceans on Earth because knowledge, work, travel or courage has brought them there. And beneath that ship, below the storm noise and the cold surface, there is another Southern Ocean entirely. Not the one of masts, engines, lifeboats and rescue beacons, but a world of krill, fish, seals, whales, squid, plankton, and strange life adapted to cold water and long darkness. The same ocean that frightens sailors also feeds some of the richest and most unusual ecosystems on the planet. Below the waves, below the ice, below the grey surface that has spent so much of our journey throwing ships around like bath toys with ambition, the Southern Ocean becomes something else entirely. It is still cold, of course. Very cold. Cold enough that most of us would prefer to experience it through a screen, wrapped in a blanket, perhaps with socks on that have never had to prove themselves in polar conditions. But beneath that cold is life. Not a little life. Not a few lonely creatures making the best of a bad address, but an entire living system built around ice, darkness, nutrients, patience, and some of the strangest adaptations on Earth. It is easy to look at the Southern Ocean from above and imagine emptiness. The surface can seem harsh and plain. Grey water, white ice, dark sky, a few birds, perhaps a whale surfacing like a slow breath from the deep. But the view from above is misleading. The Southern Ocean is not empty, it is busy. It is one of those places where the drama is not always loud or visible. Much of the work is done by tiny organisms, drifting cells, small crustaceans, fish with unusual blood, squid that move through dim water, and animals living on the seafloor where sunlight never arrives. Let us begin with the small things, because in the Southern Ocean, as in much of the natural world, the small things are holding up the larger things while receiving very little applause. At the base of the food web are phytoplankton, microscopic plant-like organisms that use sunlight to grow. They are not plants in the familiar sense. They do not have roots, stems, leaves, or opinions about window boxes. They float in the upper ocean, taking in carbon dioxide, using nutrients, and turning sunlight into living matter. When conditions are right, they can bloom in huge numbers, colouring the water and feeding the entire system above them. The Southern Ocean is rich in nutrients in many places, partly because deep waters rise toward the surface, bringing with them materials that have been circulating in the ocean depths. But nutrients alone are not enough. Phytoplankton also need light, and in polar regions, light changes dramatically with the seasons. During winter, darkness spreads over the high southern latitudes. During summer, long daylight returns, and the surface waters can come alive with growth. The timing matters. The melting and retreat of sea ice can create conditions for blooms. The mixing of the water matters. The availability of iron matters too, because in many parts of the Southern Ocean, iron can limit how much phytoplankton grow, even when other nutrients are abundant. It is a little like having flour, sugar, butter, and eggs. Then discovering the recipe also needs one tiny pinch of something you forgot to buy. Sea ice plays a role here that may not be obvious at first. We have already met sea ice as a hazard for ships, a moving frozen maze that closes routes and hides dangers. But for life, sea ice can be habitat. Algae can grow in and under the ice. When light returns, these ice-associated algae become food for small animals. Antarctic krill, especially young krill, are closely tied to sea ice habitats in many regions. Krill larvae can feed beneath the ice during winter, using it as both a shelter and a pantry. The underside of sea ice may look bare to a human eye, but for tiny grazers it can be a cold ceiling covered in food. Antarctic krill are one of the central characters in this ocean. They are small, shrimp-like crustaceans, usually only a few centimetres long, with transparent bodies and dark eyes. They do not look like creatures capable of supporting whales, penguins, seals, fish, squid and seabirds. They look frankly like something you might overlook in a tide pool. And yet in the Southern Ocean, krill are enormously important. They feed on phytoplankton and ice algae, then become food for larger animals. A single krill is small. A swarm of krill can be immense. The difference is numbers. Nature often solves scale by repeating itself many, many times. Krill swarms can contain vast numbers of individuals. They move through the water in dense groups, sometimes stretching over large areas. For predators, finding krill is finding energy. Penguins dive for them. Seals hunt them. Fish and squid eat them. Whales, the largest animals on Earth, can feed on tiny krill by the mouthful. That contrast is one of the Southern Ocean's great facts. Blue whales, humpback whales, fin whales, and minke whales may rely heavily on animals small enough to fit in your hand. A whale opens its mouth, takes in an enormous volume of water and krill, then pushes the water out through baleen plates, trapping the food inside. It is an efficient method, though not one easily copied at a dinner table. Krill are not the only pathway in the food web. Fish and squid also connect primary producers to larger predators, and different regions of the Southern Ocean have different feeding relationships. But krill are so important that changes in their abundance, distribution, or breeding success can ripple through the system. If sea ice conditions change, krill may be affected. If krill are affected, predators that depend on them may be affected too. This does not mean every animal responds in the same way, or that the system collapses from one change. Ecosystems are complicated. Animals adjust, move, switch prey, or struggle depending on the situation. But it does mean that the small crustacean drifting in cold water is not minor. It is a hinge on which much larger lives can turn. Penguins are among the most visible of those larger lives, and perhaps the easiest to love, because they walk like serious little officials late for a meeting. In the Southern Ocean and around Antarctica, different penguin species use the sea in different ways. Adelie penguins, emperor penguins, chinstrap penguins, gentoo penguins, and others depend on marine food webs, though their habitats and diets vary. Some feed heavily on krill, some take fish and squid as well. They breed on land or ice, but their food comes from the sea. A penguin colony may look like a land-based event, noisy and crowded and full of questionable social behaviour, but the colony's survival is tied to what happens below the water. Emperor penguins are especially connected to sea ice. They breed during the Antarctic winter, standing on ice through some of the harshest conditions on Earth. Their young need stable ice long enough to develop before the ice breaks up. That makes them vulnerable to changing sea ice patterns. The image of an emperor penguin may seem familiar from documentaries, but familiarity should not make the animal seem ordinary. It is a bird that survives polar darkness, wind, fasting cold, and long travel between breeding sites and feeding areas. If humans had to breed in similar conditions, most of us would quickly suggest moving the whole event indoors. Seals also depend on the Southern Ocean's cold productivity. Weddell seals, craybeater seals, leopard seals, Ross seals, Antarctic fur seals and elephant seals all belong to this southern marine world, though they live in different ways. Craybeater seals, despite the name, do not mainly eat crabs. They feed heavily on krill, using specialized teeth that help strain small prey from the water. The name is misleading, but animals are rarely consulted during naming. Leopard seals are powerful predators that eat penguins, fish, squid, and other prey. Weddell seals can dive beneath sea ice, using breathing holes and finding food in dark, cold water. Elephant seals make deep, long dives and travel huge distances, carrying information about the ocean in the movements of their bodies. Many seals look relaxed when they are hauled out on ice or land, like large wet cushions with whiskers. But in the water, they are different animals, streamlined, strong, and precise. The Southern Ocean rewards animals that move well through cold water. It is not a forgiving place for clumsy swimmers, which is unfortunate for humans but excellent for seals. Their thick blubber insulates them. Their blood and muscles store oxygen for diving. Their bodies are built around the practical question of how to survive in an ocean that would be immediately hostile to most land mammals. Whales bring another scale to the story. The Southern Ocean was once one of the great feeding grounds for immense numbers of whales. Commercial whaling severely reduced many populations, especially in the 20th century. Today, some whale populations show signs of recovery, though the history of exploitation is still written into their numbers. Humpback whales migrate from warmer breeding waters to feed in Antarctic and subantarctic waters, taking advantage of krill-rich regions. Blue whales, the largest animals ever known to have lived, also feed in these waters. To imagine a blue whale feeding on krill is to understand how the tiny and the enormous are connected without needing anything mystical. It is just appetite, abundance, and a very large mouth. There is something almost funny about the Southern Ocean being both deadly to sailors and a dining room for whales. At the surface, a storm may be throwing spray across a ship's bridge. Below, a whale may be feeding with calm purpose, doing what its ancestors have done for millions of years. Humans experience the Southern Ocean as extreme because we are not built for it. The animals that belong there experience it through bodies shaped by evolution. That does not mean life is easy for them. It means their difficulties are different from ours. Then there are the fish. Antarctic fish have some of the most remarkable adaptations in the ocean. Many belong to a group called notothenioids, which became highly successful in Antarctic waters. Some species produce antifreeze proteins or antifreeze glycoproteins that bind to tiny ice crystals and prevent them from growing inside the body. Without such protection, fish living in seawater below the freezing point of ordinary fish blood would be in serious trouble. The Southern Ocean is cold enough that water can remain liquid, while still being dangerously close to freezing biological fluids. These fish solve that problem not by wearing little scarves, though one must admire the image, but through chemistry inside their bodies. Some Antarctic ice fish take strangeness even further. Certain ice fish lack hemoglobin, the oxygen-carrying molecule that gives most vertebrate blood its red colour. Their blood can be nearly clear. This is possible partly because cold water holds more oxygen than warm water, and because these fish have other physiological traits that help move oxygen through the body. Still, it is unusual. A vertebrate fish without red blood sounds like a mistake in a biology exam, but in Antarctica, it is real. The cold has shaped life in directions that seem unlikely, until you remember that evolution does not aim for normal. It works with what survives. These fish are not just curiosities. They are part of the Southern Ocean food web, eaten by seals, penguins, and other predators. Some live near the seafloor, some occupy the water column. Some grow slowly, mature late, and are vulnerable to overfishing because their life histories are adapted to cold, stable environments rather than rapid recovery. The Patagonian toothfish, often sold under the market name Chilean sea bass, and Antarctic toothfish have drawn attention because they are valuable and long-lived. Fisheries in the Southern Ocean are managed under international agreements, but managing remote fisheries is challenging. Distance, enforcement, ecosystem effects, and changing conditions all matter. Squid also move through the Southern Ocean, though they are often less visible to us than penguins and whales. Squid are important prey for many predators, including seals, whales, seabirds, and fish. Some species live in deep water. The colossal squid, one of the largest squid species, inhabits the Southern Ocean and has captured public imagination because of its size, deep water life, and large eyes. It is not something you're likely to meet while swimming, which is good, because meeting a colossal squid would be a memorable but complicated way to spend an afternoon. Most of what happens in the deep ocean remains difficult to observe directly, so animals like these remind us how much of the Southern Ocean is still hidden from everyday view. The seafloor is another world again. The bottom of the Southern Ocean includes continental shelves, slopes, abyssal plains, canyons, ridges, and seamounts. In some places, the seafloor supports sponges, sea stars, sea cucumbers, brittle stars, worms, crustaceans, corals, and other invertebrates. Some Antarctic seafloor communities are surprisingly rich and colourful, especially in shallow or shelf regions where cold staple conditions have allowed unusual animals to thrive. Sea spiders can grow large. Sponges can form complex habitats. Slow-moving creatures can live in water so cold and clear that time seems to operate on a different biological schedule, although the animals themselves are not likely to phrase it that way. Sampling this life is difficult. The Southern Ocean is remote, deep, icy, and stormy. Much of what scientists know comes from places near research stations, ship routes, or regions that have been sampled more often. Large areas remain poorly known, especially deep-sea habitats. This is important because we cannot protect what we do not understand well. A map of known biodiversity may reflect not only where animals live, but where humans have been able to look. The blank spaces are not necessarily empty, they may simply be unsampled. In science, absence of evidence is not the same as evidence of a polite and empty seafloor. Life beneath ice shelves is one of the most surprising frontiers. Ice shelves are floating extensions of the Antarctic ice sheet. Beneath them, sunlight may be absent, and food from surface productivity may be limited. Yet researchers have found life in some of these hidden environments, including animals attached to hard surfaces far from open water. How such communities receive enough food is still an active scientific question. Ocean currents may carry particles beneath the ice. Some ecosystems may depend on sparse but steady supplies. These places are hard to reach, hard to sample, and easy to underestimate. The idea that life can persist under hundreds of meters of ice, in darkness and cold, is one of those facts that makes the planet feel larger than it did a moment before. Microbes are also essential. Bacteria, archaea, and other microscopic organisms recycle nutrients, process carbon, live in sea ice, inhabit deep waters, and take part in chemical cycles that larger animals depend on indirectly. They are not as charismatic as whales, which is unfair but true. No one is buying plush toys of Southern Ocean bacteria in airport gift shops, though perhaps someone should try. But without microbial processes, the system would not function. The Southern Ocean's life is not only the visible animals, it is also the unseen metabolism of the sea. The cold shapes everything. Metabolism tends to slow in cold environments. Growth can be slow. Reproduction can be seasonal. Many animals have long lifespans. Some have specialized enzymes that work efficiently at low temperatures. Cell membranes must remain functional in the cold. Proteins must fold and operate properly. Antifreeze compounds prevent freezing. Bodies are tuned to a narrow range of conditions. That specialization is impressive, but it can also create vulnerability. If water warms, acidifies, or changes in oxygen, species adapted to cold stability may not respond easily. The Southern Ocean is harsh, but for its native life, it is home. Change the home too quickly, and even well-adapted animals can struggle. Ocean acidification is one concern. As seawater absorbs carbon dioxide, chemical changes make it harder for some organisms to build and maintain calcium carbonate shells or structures. Cold waters can absorb more carbon dioxide, and polar regions may be especially sensitive to acidification. Some planktonic organisms, pteropods for example, have delicate shells and may be affected by changing chemistry. Pteropods are sometimes called sea butterflies, which sounds gentle and lovely, and they are indeed small, drifting animals with wing-like swimming structures. They are also food for fish and other animals. A tiny shell, dissolving more easily in changing seawater, can become a much larger ecological issue. The Southern Ocean's living system is therefore both resilient and vulnerable. It is resilient because life has adapted to cold, darkness, ice, and seasonality in astonishing ways. It is vulnerable because many of those adaptations are tied to specific conditions. Sea ice timing matters, water temperature matters, food timing matters, predator and prey overlap matters. If phytoplankton blooms shift, if krill recruitment changes, if sea ice becomes less predictable, if warming water enters habitats once kept colder, the effects can move through the food web. Not always simply, not always immediately, but they can move. There is also human use. Krill fisheries operate in parts of the Southern Ocean, mainly supplying products such as aquaculture feed, omega-3 supplements, and other uses. Toothfish fisheries operate under regulation. Tourism brings ships and visitors. Research brings activity too, though for different reasons. International management in the Southern Ocean is unusually important because the region is remote and shared. No single nation owns the open Southern Ocean. Cooperation is needed to manage fishing, protect ecosystems, reduce impacts, and respond to change. As usual, the hardest problems are not only scientific, they are also political, economic, and practical, which is nature's way of making sure no meeting ends early. Still, there is hope in knowledge. The more scientists learn about krill, sea ice, fish, whales, microbes, and benthic habitats, the better the world can understand what is at stake. Satellite tracking shows animal movements. Acoustic surveys detect krill swarms. Autonomous floats measure water conditions. Tags on seals and whales collect data as the animals dive. Remotely operated vehicles explore seafloor habitats. Genetic methods reveal hidden diversity. Each tool adds one small piece to a very large puzzle. The Southern Ocean does not give up its secrets quickly, but it does give them up slowly to patient work. And perhaps this is the most surprising thing about the Southern Ocean's life. It thrives not in spite of the cold, but through adaptations to it. The ice is not only a threat, it is habitat. The darkness is not only absence, it is part of a seasonal rhythm. The rough water is not only danger, it mixes nutrients and supports productivity. The same ocean that can humble a ship can feed a whale. The same sea ice that can trap a vessel can shelter krill larvae. The same cold that would endanger a human in minutes has shaped fish with antifreeze in their blood and seals that dive beneath frozen surfaces. So when we imagine the Southern Ocean, we should not leave it as a grey ring of danger around Antarctica. We should fill it with movement, krill swarming under the ice, penguins diving with quick turns, seals slipping through dark water, whales feeding in the summer light, fish moving slowly near the sea floor, sponges filtering water, microbes doing quiet chemical work, squid passing through the deep, albatrosses above riding the wind, connected to the sea by every meal they take from it. The Southern Ocean is dangerous, yes, but it is also alive in ways that are strange, practical, delicate, and deeply connected to the rest of the planet. Its life depends on cold, ice, current, and season. Its food webs connect the smallest cells to the largest animals. Its hidden seafloor may still hold species humans have never seen. And as the climate changes, this cold living world becomes not just a remote wonder, but a warning system, a research frontier, and a major part of Earth's future. Because the Southern Ocean is not only a place where ships struggle and storms gather, it is one of the great working parts of the planet. It stores heat, it absorbs carbon, it moves nutrients, it helps drive circulation, it feeds life on a vast scale. And to understand why this dangerous ocean matters beyond its own cold borders, we need to look at the role it plays in the whole Earth system, from the deep ocean to the air above every continent. Every breath we take feels personal. It belongs to the room we are in, the air around us, the quiet rise and fall of the body as the day slowly loosens its grip. But that air is part of a much larger system. It has moved over forests, deserts, cities, mountains and seas. It has crossed borders without needing a passport, which is efficient, if a little rude, to customs officials. And far to the south, around Antarctica, the Southern Ocean is constantly exchanging with that air, taking in heat, releasing cold, absorbing gases, and helping shape the climate of the whole Earth. This may be the most important thing to understand about the Southern Ocean. It is not just a remote ring of dangerous water at the bottom of the map. It is not only the place of roaring winds, giant waves, drifting ice, shipwreck stories, krill swarms, and whales feeding beneath grey skies. It is one of the planet's great regulators. It is a working part of Earth's climate system, and although most people will never see it, everyone lives on a planet shaped by what happens there. That can feel strange at first. The Southern Ocean seems so far away from ordinary life. It is far from morning traffic, kitchen lights, school buses, office chairs, garden fences, and the small daily rituals that make up a human week. It is hard to imagine that cold water around Antarctica has anything to do with a warm evening in Europe, a dry season in Africa, a storm track in the Pacific, or the sea level near a city thousands of miles away. But the Earth does not work in neat little boxes. The ocean, the atmosphere, the ice, and living things are connected. What happens in one part of the system can move through the rest, sometimes quickly, sometimes slowly, sometimes so slowly that people mistake motion for stillness. The Southern Ocean matters first because it absorbs heat. Since humans began adding large amounts of greenhouse gases to the atmosphere, the planet has taken in extra energy. Much of that heat has gone into the ocean. The ocean is vast, deep and slow to warm compared with the air, which makes it a powerful heat reservoir. The Southern Ocean in particular has absorbed a very large share of that excess heat. It does this partly because of its unique circulation. Winds around Antarctica stir and drive the surface waters. Deep waters rise toward the surface. Other waters sink. Heat can be moved downward and stored away from the atmosphere, sometimes for long periods. This heat uptake has helped slow the warming we feel at the surface. That may sound comforting, and in one sense it is. The ocean has buffered us. It has taken in heat that would otherwise have remained in the atmosphere. But buffering is not the same as making the problem disappear. Heat stored in the ocean is still in the Earth system. It can affect marine life. It can melt ice shelves from below. It can change water structure. It can influence circulation. It can remain hidden for a long time, then return toward the surface in ways scientists are still working to understand. The Southern Ocean is not a magical cupboard where extra heat can be put away forever, along with old chargers and the instructions for appliances no one owns anymore. The Southern Ocean also absorbs carbon dioxide. When carbon dioxide builds up in the atmosphere, some of it dissolves into seawater. The global ocean takes up a substantial amount of human-produced carbon dioxide, and the Southern Ocean plays an unusually large role in that process. Cold water can hold more dissolved gas than warm water, and the circulation around Antarctica helps move carbon into deeper layers. There is also a biological side. Phytoplankton take up carbon dioxide during photosynthesis. Some of that carbon moves through the food web, some eventually sinks as particles, waste, or dead organisms carrying carbon downward. This is often called the biological carbon pump, which sounds like something that should have a switch and a small warning label, but is really a vast set of natural processes happening cell by cell, meal by meal, season by season. The physical and biological pumps work together. Surface waters exchange carbon dioxide with the air. Currents move water sideways and downward. Tiny organisms turn dissolved carbon into living matter. Animals eat, breathe, migrate, and die. Some carbon returns quickly to the atmosphere. Some sinks into the deep ocean. Some may remain away from the air for centuries. The Southern Ocean is one of the great places where these exchanges happen. It is not simply absorbing carbon like a sponge. It is processing carbon through motion, chemistry, biology, and depth. But there is a complication, because of course there is. A system that absorbs carbon dioxide can change as climate changes. Winds may shift. Ocean layers may become more or less mixed. Upwelling can bring deep carbon-rich water back toward the surface, where some carbon dioxide may escape into the atmosphere. Warming can alter how gases dissolve. Changing sea ice can affect light, mixing, and biology. This means the Southern Ocean carbon sink is not a fixed machine. It varies over time. Scientists study it carefully because even small shifts in its ability to take up carbon can matter for the global climate. This is one reason research programs send instruments into such difficult waters. Ships, floats, gliders, moorings, satellites, and animal-borne sensors all help scientists measure temperature, salinity, oxygen, carbon, currents, nutrients, and ice. An autonomous float bobbing in the Southern Ocean may not look dramatic, especially compared with an iceberg the size of a city, but it is part of a major effort to understand the planet's future. It drifts, sinks, rises, records, transmits, and goes back down again, like a very dedicated employee with no interest in office gossip. The Southern Ocean also matters because it connects the surface ocean to the deep ocean. In many parts of the world, the upper ocean and deep ocean are separated by layers of different temperature and density. Around Antarctica, strong winds and unique circulation patterns help bring deep water upward. This upwelling is one of the defining features of the region. Deep water that has been out of contact with the atmosphere for a long time can rise toward the surface. At the same time, cold, dense waters can sink near Antarctica, feeding deep and bottom water masses that spread into other ocean basins. This overturning circulation is part of the global ocean's slow movement. It helps distribute heat, salt, oxygen, carbon, and nutrients around the planet. It is sometimes compared to a conveyor belt, though the real ocean is much messier than any conveyor belt found in a factory. It swirls, mixes, splits, sinks, rises, and responds to wind, ice, temperature, salt, and the shape of the seafloor. Still, the comparison helps. The Southern Ocean is one of the places where the conveyor connects levels, where deep water and surface water meet, where the hidden ocean speaks to the air again. Nutrients brought up from the deep help support life near the surface. These nutrients can feed phytoplankton blooms, which in turn support krill and the wider food web we have just wandered through. So the Southern Ocean's circulation is not only a climate process. It is also a biological process. The movement of water helps determine where life can flourish. A current may carry nutrients, a mixing event may bring food into the light, a sea ice retreat may open water for a bloom, a change in winds may shift the timing or location of productivity. In the Southern Ocean, physics and biology are not separate stories. They are two narrators taking turns, occasionally interrupting each other. Sea ice adds another layer to the whole Earth story. Antarctic sea ice expands and retreats each year, reflecting sunlight when it's present and exposing darker ocean when it melts back. Ice and snow reflect much more incoming sunlight than open water. Dark ocean absorbs more energy. This difference, called albedo, influences the energy balance of the polar climate system. When sea ice changes, it can affect how much heat the ocean absorbs, how much moisture and heat move between ocean and atmosphere, and where habitats form for ice-associated life. Recent Antarctic sea ice behaviour has been especially concerning and scientifically puzzling. For decades, Antarctic sea ice did not follow the same simple pattern of decline seen in the Arctic. It varied strongly by region and year, with periods of increase in some places and decrease in others. Then, in recent years, very low Antarctic sea ice extents drew attention. Scientists are working to understand the roles of winds, ocean heat, storms, fresh water, natural variability, and climate change. This is not a small side issue. Sea ice affects ecosystems, climate feedbacks, ocean mixing, and even how waves interact with the polar environment. A change in ice cover is not just a change in scenery. It changes the way the ocean breathes, reflects, shelters, and moves. Then there is the ice on land. Antarctica holds enough frozen water to change global sea level dramatically over long time scales. The Southern Ocean matters because it touches the edges of that ice. Warm, deep water can reach parts of the Antarctic continental shelf and interact with ice shelves from below. Ice shelves are floating extensions of land ice, and they act like buttresses, helping slow the flow of glaciers into the sea. When ice shelves thin or weaken, the glaciers behind them can flow faster, adding more ice to the ocean and raising sea level. This does not happen evenly all around Antarctica. Some regions are more vulnerable than others. West Antarctica, in particular, has areas where warm water reaching ice shelf cavities is a major concern. East Antarctica also has vulnerable sectors, though the story there varies by region. The point is that the Southern Ocean is not simply next to Antarctica. It is actively involved in Antarctica's future. Ocean heat can reach ice. Ice melt can freshen the ocean. Fresh water can affect density and circulation. Circulation can influence how much heat reaches the ice. Everything loops back into everything else, which is fascinating unless you are trying to make a simple diagram, in which case it becomes mildly personal. Sea level rise connects this remote region to coastlines everywhere. A glacier losing ice in Antarctica does not raise sea level only beside Antarctica. Meltwater enters the global ocean. The effects are felt by low-lying islands, coastal cities, deltas, ports, wetlands, and beaches around the world. A process beginning beneath an Antarctic ice shelf can become part of a flooding problem far away. This is another example of how distance can deceive us. The Southern Ocean may be far from most human homes, but it touches the world through water. weather and climate patterns can also be influenced by Southern Ocean changes. The Southern Ocean is a huge boundary between atmosphere and sea. It absorbs heat, releases moisture, drives storm tracks, and helps shape temperature gradients. Changes in its surface temperature, sea ice, winds, and circulation can influence atmospheric patterns in the Southern Hemisphere and beyond. The exact connections are complex and vary by region, but the broad lesson is clear. This ocean is not isolated at the bottom of the world. It is part of the engine room. The Southern Ocean's ecosystems matter globally too. They are not only beautiful or unusual, they are part of the carbon cycle, the food web, and the biological richness of the planet. Krill connect microscopic producers to whales, seals, penguins, fish, squid, and seabirds. Whales feeding in the Southern Ocean migrate to other waters, carrying nutrients through their bodies and waste. Seabirds travel enormous distances. Fish and squid connect deep and surface food webs. Even dead organisms sinking into the water column help move carbon downward. Life is not decoration on top of the climate system. Life is involved in it. This is why changes in the Southern Ocean raise concern beyond the fate of individual species, though individual species matter too. A decline in krill in one region could affect penguin breeding success there. Changes in sea ice could affect emperor penguins, seals, and krill larvae. Warming and acidification could affect plankton and shelled organisms. Fisheries must be managed carefully because removing too much from one part of the food web can have effects elsewhere. The Southern Ocean may look large enough to absorb any impact, but size does not remove vulnerability. A large system can still be pushed. International cooperation is essential here. Antarctica and the Southern Ocean are governed through treaties and agreements, unlike those in most parts of the world. Scientific cooperation, environmental protection, fisheries management, and tourism rules all matter. No single country can protect the Southern Ocean alone. The ocean itself circles the planet, which is a fairly strong hint that it does not belong to one flag. Its problems cross borders, its benefits cross borders, its protection must cross borders too. There is something rare about that. The Southern Ocean asks humanity to think at the scale of the planet, not just what can be taken from this place, not just how can a ship survive this crossing, but what does this place do for everyone? How does it store heat? How does it absorb carbon? How does it support life? How does it influence ice, sea level, weather, and future climate? These are not small questions, but they are practical ones. They matter for farms, cities, coasts, fisheries, ecosystems, and future generations who may never see Antarctica except in photographs. And yet, after all this science, the Southern Ocean remains more than a set of functions. It is not only a carbon sink, a heat reservoir, a circulation gateway, a sea ice factory, or a nutrient engine. Those phrases are useful, but they can make the ocean sound like industrial equipment. It is also a place, a real place of wind, cold, birds, whales, ice, darkness, summer light, drifting flows, deep water, and long swells moving beneath southern skies. It matters because of what it does, but also because it exists as one of the last great wild marine regions on Earth. There is a quiet humility in studying a place like this. The more we learn, the less simple it becomes. The Southern Ocean can slow warming by absorbing heat, yet that stored heat can threaten ice shelves. It can absorb carbon dioxide, yet the strength of that carbon sink can vary. Sea ice can protect and shelter life, yet changing ice can disrupt ecosystems. Strong winds can make the ocean dangerous, yet those winds also help bring nutrients upward. The same features that make the Southern Ocean severe also make it important. Danger and importance are intertwined. So perhaps the Southern Ocean's greatest lesson is connection. The wave that batters a ship is connected to wind belts shaped by planetary circulation. The krill beneath sea ice are connected to sunlight, nutrients, and ice conditions. The carbon entering cold water is connected to human activity far to the north. The heat stored below the surface is connected to atmospheric warming. The ice shelf melting from beneath is connected to sea level on distant coasts. The Southern Ocean circles Antarctica, but its influence does not stay there. It moves outward through water, air, ice, and life. And now, after drifting through its winds, currents, waves, ice, ships, storms, and hidden ecosystems, we arrive back at ourselves. Not because the story ends neatly, but because every story about Earth eventually returns to the people listening. We began with danger, the world's most dangerous ocean, a place of huge waves, violent winds, freezing water, floating ice, and long empty distances. And yes, the Southern Ocean has earned that reputation. It is not gentle with ships, it is not easy for sailors, it does not offer many second chances, but danger is only one part of its identity. It is also one of the most important oceans on Earth. It helps regulate the climate. It helps move heat and carbon. It feeds extraordinary life. It shapes Antarctica's future. It influences sea level, ecosystems, and global circulation. It is far away and deeply connected. It is harsh and productive. It is frightening and necessary. It is, in its own cold way, one of the planet's great caretakers, though perhaps not the kind that brings you a blanket and asks if you would like more tea. So, the next time you see Antarctica at the bottom of a map, do not let your eyes skip over the blue ring around it. That ring is not empty space. It is motion. It is weather. It is memory stored in deep water. It is carbon slipping below the surface. It is krill under ice and whales returning each summer. It is storms circling the globe and waves travelling through darkness. It is a place most of us will never visit, but a place that helps shape the world we wake up in. And so, dear listener, we have come to the far southern edge of our quiet voyage. We have followed the Southern Ocean around the planet through the winds that roar, the waves that rise like moving walls, the ice that drifts and closes like a frozen maze, the ships that dared to cross it, and the strange life that continues beneath its cold surface. We have seen that its danger is not a single thing, but a combination of wind, water, distance, ice, and cold. And we have seen that its importance is just as layered, reaching from tiny plankton to global climate, from Antarctic ice shelves to coastlines far away. If you have found this journey calming, interesting, or just a steady place to rest your thoughts for a while, I would be ever so grateful if you gave the video a like, maybe subscribed, and shared this quiet corner of science with someone else who might enjoy drifting off through the wilder parts of the world. The Southern Ocean may be restless tonight, circling Antarctica under clouds, stars, snow and wind. But wherever you are listening from, you are safely here, in this moment, far from the breaking waves and floating ice. Sleep well, fellow traveller, and while the cold ocean keeps turning at the bottom of the world, let your own thoughts grow still, soft and warm.